So we'll start with the session. Greetings to all present here. We welcome you to the Algorithms Festival hosted today by Database Club and ACMW Student Chapter. Today is a day to delve into the joy of algorithms and to appreciate the products of years of intellectual pursuit.
Today is not just about learning, it's about celebrating the beauty of computation, uh, years of progress in computer science. Throughout the day, we will explore a variety of topics, each one showcasing the power and elegance of algorithms in shaping the way we solve complex problems. Whether you are here to learn, to present, or simply enjoy the experience, we hope you leave with a deeper appreciation and role of algorithms in our life.
Today we are also here to celebrate a figure who inspires many to tackle profound mathematical and computational challenges head on. This year marks 70 years of Professor Pandurangan. I would like to invite Professor Pandurangan to share some words of encouragement with us.
Yes, it's customary to begin the session with a prayer. The best prayer is saying the gratitude. First of all, I would like to thank from the bottom of the heart the chairman of Computer Science and Automation Department, CSA department. I requested the facility of this hall at 12:02. The approval came in 12:03. Hardly I would have pressed the send key, and before even reviewing whether the mail has gone or not, I got the approval from them. Rajiv, who's a chairman of Kotak Mahindra AI and ML research activities and research center, has also given the same real-time support for this activity. The moment I proposed then that the students have come forward to organize a workshop of this kind, immediately all the logistics related to that he has approved. This is the level of encouragement that uh, we are getting. Okay, we always have our program coordinator, Deepak, and our UG dean, uh, Professor Srikant. Uh, all these people, they are helping us day in and day out, directly and indirectly, to carry out the intellectual pursuits. I have told many of you in several forums that the distinguishing feature of the Indian Institute of Science UG program is the interdisciplinary flavor of this. In typical IITs or in other system, computer science is a department. It is a compartmentalized wall and a small building or a small unit is what would be responsible for classroom, laboratory, and everything related to that. Whereas if you look at the genesis of this program, it has been started with four departments coming together, and it is continuing to be an interdisciplinary activity. Not only that, you can see that the students can freely move around, take up project, interact with various departments depending on their interest and other things, and they get a warm, unconditional support from all quarters of the institute. Basically, people belong to the institute and not to the department. Department is just a very small identity for some minor administrative purposes. However, the sense of belonging, okay, and similarly, when undergrads are welcome, the director would present the national impact of the research carried out by IISc. He'll start with the major water problems that are solved by the IIT research. Two undergrads who are coming to join computer science department. That shows the vision of the institute. And that vision is properly represented in this collection of talk. This is not something which is a part of any core course or any textbook material or an extension of it. These people have gone all over the range of topic, the range of subjects that has been touched upon is astounding. This is simply phenomenal. And they have taken a lot of effort to gather the material, information, understand, write slides, rehearse it, and rehearse again, and make sure that a good consolidated presentation of the ideas are to be presented for them, presented to the audience. I heartily thank the enthusiasm shown by the undergrads here, the third semester students, and as they have been joined by a fifth semester students also. Right now they are writing some examinations. Soon they will all join here. We have a talk by the senior student. That's the first batch student, and these are the second batch students. And they have come here to do something really exceptional and completely outside the syllabus of any of the course. And that's the way you have to do for going beyond the textbook and then build the research enthusiasm. We had a paradox festival so enthusiastically conducted and done by the senior batch of the students, or the first batch of the students, and following the footstep and their inspiration by them. Here is another festival, Algorithms Festival. These students have undergone a course on discrete math, some basic system courses, and then some math courses. And just now they have started learning about the algorithms and the beauty of algorithms and very clever ways of solving the problem. In spite of the fact that they got only a very recent start, the level at which the individuals have gone on to read more, learn more, understand more, and then attempting to present them is really heartwarming. I just casually mentioned in one of the classes that was the day before I was turning 70. So it was the last day of 69th year of my existence. And I told them that this is tomorrow is a birthday. And many of my friends and other colleagues who have been sending the wishes, who knew me, they call it as this year is going to be a Pandu at 70 year. So there are some special programs were organized in Boston and in Bay Area, where my past students were all around. And I never expected that here also, with such a love, affection, and enthusiasm, uh, they added a tag on Pandu at 70 for this event. To that, personally, I would like to thank all the undergraduates for that. This is just a personal note. Beyond this small personal note, the event is going to be really exciting. It's going to be an eye opener. It will set standard for your next batch of students to follow. Right? We are going to have a lot more innovative, thematic research presentations in the days to come. Right? It's just that I happened to get connected with the undergrads at a very early stage. Right in the second semester, I teach discrete math, and then in the third semester, algorithms. Of course, as you go advance, you're going to meet so many faculty members who have broad spectrum of research area and interest. And I'm sure we can have very interesting and exciting thematic topics in several of the emerging areas. This is just a beginning. This is sampler. This shows what we are capable of, and we have to convert this potential to success. We have data-based, such an enthusiastic group of students volunteering to do a lot more than the regular academic work. And the ACM Women's Wing is also doing a lot of exciting work, and they are very happy to participate in these kind of activities and then build uh, several academic activities. So, with heartwarming thanks to the database and as well as ACM Women Wing, and for every speaker and to the entire undergrads and to the audience who will be here and who are going to be here and who will participate in this, I would like to extend my warm welcome and hearty thanks. And this is the prayer that I would like to say at the beginning of. Normally, vote of thanks is done at the end of the function. I somehow believe that it has to start with the thank, because nothing of this scale and breadth happens without the enthusiastic participation of the students, support from the system, help from senior faculty members and administration. All of them have come together, and therefore now success is a corollary and not a theorem here. So, with these few words, once again, I warmly welcome all of you. Participate, enjoy the sessions, learn a lot, interact with the speaker and students. And with this, I would like to conclude my presentation. There is only one request. There's another form of prayer that we all should adhere to. Okay, this I heard in Japan, which is known for punctuality. Punctuality is prayer. It's a striking statement when I heard for the first time. In fact, when people like us who are slightly laid back and other things, when we go there, we are racially discriminated. They are so punctual on up to the last minute. And when there is an earthquake and if the trains slow down, and because of that, if it is delayed for 1.5 minutes, they apologize for a delay of minute and a half. And that really, opened up a different kind of perception and life and attitude. The fellow beings time, how we should care about others. When somebody is spending some time, that means they show their intention to be with you for whatever. So it's very important that punctuality is a prayer, and the speakers must adhere to the time slot that is given to them. Be conscious about the time, and then the further speakers and follow up of the event and other things. Stick to the punctuality and time bounds, and make the event crisp, exciting, beautiful, and wonderful. And adhering to the time is really important and one factor of that. With that request, let me conclude my talk. Thanks once again to all of you, and warm welcome to you. Thank you.
Now I would like to invite Himanshi and Agrim on the stage to guide us through this amazing festival session.
Thank you, Professor. Distinguished guests, esteemed constituents, I would really request Pratham Sahaj Foundation to start.
So,
Yeah.
analysis on data. However, sharing data across communication channels could be quite risky. So today, I, Sahaj, and my teammates, Pratham and Krishna, are here to explain you about a simple, secure multi-party computation protocol on performing computation on inputs on sensitive data while preserving their privacy. So today, in this session, we will delve into the Yams millennia problem, followed by oblivious transfer and a private key encryption scheme, key exchange protocol, the Diffie-Hellman protocol.
You just got a DSC marks. How much did you get?
I got very bad marks.
One thing over. Well, why you can do you got this?
Better than this.
So you guys want to know which one of you got 3 marks in DSC? So maybe both of you can tell me your marks and I can let you know.
No, we can't trust.
So basically we can generalize this problem. So suppose we have two numbers A and B. Suppose your marks are A and suppose Krishna your marks are B. So generalizing this, we need to find out whether A is greater than B or B is greater than A. How actually revealing both of the two values. So in the ideal model, both of the parties can tell me. So tell me the underlying values. Yeah, so in that case, I have as a positive third party. Then what is the common way that a positive third party will actually be tested? It is malicious. So in the real model, we come up with a protocol. The parties need to follow honestly plan exchange information without revealing anything. So here what we can do is we can take deck of cards and we can firstly encode the command as following. So if we have a client on one heart, we can refer it as the heart. And if we already have a command by a client, we call it as a heart. So what we first need to do is we need to encode Krishna's marks using the following command. So what you can do is you can take Krishna, you can take eight black cards and arrange it in a sequence. And then followed by you can take 26 minus 8 red cards and arrange it beside them. Now what you can do is you can flip them over such that nobody in the audience as well as some can see your sequence. But the value of A remains unknown to everyone. Now we can give the deck of cards to Pratham. Now what you can do is you can probably take the pH pair of pH pair which is your marks. Take the pH pair, right? Permute it to the first as the first pair in the sequence of cards. So basically, Python uses performance of Carlo permutations and this guarantees the secrecy of the value of B. Now, we will reveal the first pair of cards. So, if the revealed cards is a red card, which we encoding as follows, then we conclude that B is greater than A, that is Krishna has greater marks in the DSA exam. If the revealed card is black, then we conclude the opposite, that is A is greater than B.
Pratham got. To summarize what here was, since first I explained an ideal model in which there was a trusted third party, and you could run a mass parties in the group. So we were going to this where we conducted some scheme and we ensured our result. But in that case, we assume that the private competition form performed by Pratham in the end, when we moved the BH pair to the first pair, was honestly. But what if we cheated? No one knows that, right? we need to ensure the security of such kind of protocols as well. See, Pratham could have cheated. So now, what does it mean to be secure? To understand that, we need to understand what are the different kind of adversaries. First of all, there is the connect adversary, which will trigger the protocol as is devised. The protocol will finish, but he might not do it as was planned or as was devised to it. Just that when Python conducted the final random permutation, he could have had some previously planned permutation in his mind. He could have done that secretly, and the result would have been corrected. The second kind of adversary would be honest with QBs. That would be that he or she will conduct the protocol as is device as is planned. But in the middle, they can seek information which was not supposed to be known. The third kind of protocol, the adversary, which is the most notorious type of adversary, is they can anything during the protocol. They can even crash the protocol. Some could have took the protocol and thrown them on well, just ending the protocol at once. So now we move on to the distinction between real and ideal protocols. The ideal protocol, which is the trusted third party, was secure against all these things because there was no interaction between the two parties. But in the real protocol, it was not the case. To ensure the security of the real protocol, we need to ensure that the attacks that the ideal protocol is secure against. The real protocol should also be secure against those attacks. Okay, now let's move on to a very interesting case study. Suppose there is a mobile phone company and it has launched a new model recently. After 1 or 2 weeks of sale, a customer sues the company that it is causing some kind of related problems to him. So the court orders, so the case goes to the court, and the court orders that, okay, if we need to ensure who's the one at fault, let's do one thing. If the company is coming this, when you take there's a given list of hospitals, you can insurance list of them, the ENT department of of those hospitals, and what we can do is we can match the number of people that are common in those lists. In that, suppose there are lots of phones sold. If 1 or 2% were reported ear-related problems, then there might be some minor problem in the people. But if 25% or 50% of the problems, then there will be some issue with the phone. In the company's report. So this comes into the concept of private sector decision, where we have two data sets, the company's buying list and the list of the ENT department and the data set of the ENT department of the hospital. But the thing here is we need to ensure data privacy. None of us want our medical history to be written to a phone company. Right? So in that case, we'll ensure that our data remains secure using something that Seth will explain now.
So, uh, so basically, we use the paradigm of secure multi-party computation in order to ensure the privacy of the data because none of the phone company as well as the hospital communications would like the details to be out in the public. So, hospitals now need a trusted third party in carrying out this protocol. So, generalizing this problem, and parties, which P parties are involved. The value of P is valued by the third party that we are going to zero. So each party plus final input P of the value. And what we need to do is we need to complete the function of one of these input values. And our objective is that all of the parties involved only get to know the the function. And each right apart from the should not be released.
Another very interesting case to me. Suppose there is some international conflict going on between two countries. So the motive of the United Nations is to solve those conflicts. So the United Nations General Assembly convenes and they decide all the countries they tell all the countries to vote for one country or the other. But the thing here is every country wants to maintain the diplomatic relations, right? No one wants to have conflicts with countries they don't want. So now the thing here is everyone can vote, but they don't want their votes to be known. We want the sum of the votes. Who won? So in that case, again, we have to kind of say one solution would be again, we have a trusted third party, and such as the chairperson of the UN General Assembly. The usually wants to the chairperson, he wants to vote, and he engage the judge. And another solution would be securitization, which comes under secure multi-party conversion. Yeah. So to generalize this in a more mathematical form, let's say we have two countries. If we have a vote which is equal to the value of 0 or 1. What we need to do is we need to compute the sum. with all those big values. So yeah, again, if the chairperson wants to start world with me, he might even just send all the votes in the report. But if it doesn't, so we need a secure protocol, right? We cannot trust the third party. So the countries might decide among themselves. What we can do is we can create private channels in each other to which we communicate secretly, that no one can intercept. And we decide on a common value n, which is greater than the number of countries. Now we put all the operations pointing on one. So we in the ZC, all the values are integers between 0 and 9, if not included. So we compute the sum using a secure protocol, which says that suppose for simplicity, 4 countries. The first country chooses some random number, and since there are 4 countries, n can be 5, is greater than 4. So the first country chooses some random number k in the set z sub 5. It adds that random number to its own vote. It passes on that vote to the second country. The second country adds its own vote to the value c1. The bit b2 is added to c1. It passes on c2 to the third country. The third country adds its own bit value b3 and passes on c3 to the fourth country. The fourth country adds its own vote and passes it back to the first country. The first country can what the first country can do is now you got C4. You can just subtract A from C4. You finally obtain the sum yes. And finally you can know which country was at fault in the past. Yeah, so this is the formalized version of the algorithm that we just explained. Now the thing is, the aim of the entire scheme was that no country should learn anything apart from their own vote and the sum of all the votes. Any information that they can infer from that should be the only information that they can infer through this protocol. And we can ensure that this is the thing, and no extra information was revealed, even though some extra numbers were exchanged.
So now we'll move on to a way of doing secure multi-party computation generally. So there is a protocol called oblivious transfer. Basically, what it means is we need to transfer some data from person A to person B with the person A knowing which information was sent. Like, give you an example. Let's say it was, let's start a unit tutoring question bank. So, like, students can come to me and they can ask for study material in, let's say, maths and physics. So, but the student does not need to know whether he is using mathematics or he is using physics. So, basically, the goal is that if a professor in the study material, if he specific subject, he will know which study material was sent to him. So, this is a problem that comes under oblivious transfer. So, the most basic form of oblivious transfer can be where you have two information in the party A, M0 and M1, and the party B wants to replace some M2, maybe 0 or 1. So you can achieve this using again the trusted third party. So Alice gives the M0 and M1 to the trusted third party, and Bob gives his value B to the trusted party. He receives the information M from the trusted third party. But again, in real life we don't have third parties. So how do we achieve this? So now to do it computationally, we need to assume few things. So first we assume that the problem of discrete law, which is b ratio of x formula x is the b to the power x is a only how to use the compute. So for example, we want to find x such that 3 ratio of x is 117. Anyone in audience want to like say how would they figure out? Huh? Okay, but like it's 7. Okay, so yeah, like in general, if we choose the values b and m carefully, we cannot use like mathematical theorems nicely. And like the best we can do is almost like brute force through the whole like space. So we can compute all the powers of 3 and then find which value becomes 1 more 7. Here it is 6. So, like, this problem becomes very hard for very large values of M and G if they are taken carefully.
So the matter Multiparty is based on a lot of assumptions from the complexity theory. One of the assumptions is the existence of binary functions. This as from the name, we can present binary function is that it is easy to work with input data. Once the output computationally easy, that solve binary problem, you can output given a column input. We want output computationally fine. So basically, there is an underlying assumption that the thing is not equal to Monte, which is probably one way. So based on these assumptions, you can do the following procedure. Fill the information securely. So let's say we start with a final field graph. Element in random element G. So these are known to all the parties and even maybe a third party. So now sending generates a random number A, the receiver generates a random number B. And we share the values capital F, capital B, which are G rational A and G rational B to each other. If these small a and small b are not possible to find, these cannot be found by the other parties because it's assumed that it is very hard to find A and B because it's discrete law. So now these values can be used. So like the sender has the value B, which is G rational B. So this can be raised to the power A, which is known to sender, to compute B rational A, which will become G rational AB. So this value is common to both of them. So this value can be used to now generate a key and include the message securely. So this including message can now be sent over any channel. So this class can be intercepted by any other. So now, since we have a way of sending encrypted messages, we can generalize, we can use the same protocol to obvious transfer also. So now, this means sender generates a random number and sends capital A, which is G rational A, to the receiver. So, depending on the receiver also obtain information M0 M1. Since given are these two things, since equal to 0, this means D raised to B. And if C becomes to 1, then he says A times D raised to B. So now, sender will complete two keys. One will be B raised to A's one-way function, and second one will be B by A's one-way function. So now, in the M0 and M1 messages, will be encrypted using M0 and K. So now, if C was 0, then the message that was encrypted by G user AD will be page views. Then if C was 1, then the message that is encrypted by G user AD will 1. So now, since they both can agree on a common key, which is G user AD, uh, finally the receiver can decrypt either of any of these messages to find its answer. Now, since as from both of the messages, she doesn't know which message got transferred to the receiver. So this is an obvious answer where sender does not have any information which information was sent, but the receiver got the information it wanted. Move on. Because if receiver wants to decode the value, that's not really very fast. Doing some mathematical stuff, this will become clear, which I encourage all of you to try on your own.
Okay, coming back to Pratham's company. So the thing here was that right now we are discussing about 1 out of 2 box, where similarly, if I am weak in maths or computer science, I can just send my subjects through a program and he can give me a problem set according to that. You can generalize this towards a 1 out of n box obvious transfer. In which case, if I'm weak in integration, I used to be weak in integration. So if I'm weak in integration, I can just send that value to Pratham and he will give me a prediction related to integration only. Now we can also generalize this further towards 3 out of n box of obvious transfer. where I want K informations and I can send the request for them without knowing which K informations I want. Pratham will send me the informations that I want. Yeah, and we previously discussed the mobile phone and hospital exam. This is one of the solutions for that. Using we can perform private sector intersection using the KNF sandbox or Bluetooth transfer. And with that, we'd like to conclude. Thank you very much. How do you do the intersection?
So, like, so one way you can think kind of is like, let's say we have list of like people, M0, M1, dot, dot, dot. So now, so we need to go in a little bit more details. Like there, basically we can compute any function. Like in the secure multi-party computation, any function can be evaluated. Uh, but we need to go in bit more detail, which we skipped one topic, which is Harvard circuits. Using that, we can find a way to compute any function uh, using oblivious transfer. So what happens in that case is you have a function which is a Boolean function, and from that you can generate like all pairwise inputs to output corresponding values. Once function gets encrypted using cryptographic values, and then we can do oblivious transfer to find the specified value that we want to find. So there is one thing you can read about, which is Harvard circuit, which completes the whole thing to do all the secure multi-party computations. Yes.
What if receiver doesn't know in what order the send goes?
Doesn't matter. So the receiver will try to decrypt both of them. The only value which gives something sensible will be the one which is decrypted by that key. So like we can have something attached to the message, which like we can check if the first something bits are something, then we can check. But that might also introduce some like issues in security, because now you know the key which decrypts need to give those values. So to, like basically what we want is we'll try on the things that are given, and the only thing that makes sense will be the answer.
Yeah. So the point is that if we had sent capital B equal to G power B, then he will be able to decrypt only E0. He will not be able to decrypt E1. Because a value that is constructed K0 and K1 is depending on the values that are set. So what happens is that K1 and K0 will come to receiver. Right? Sender actually encrypts all the information that is available with him and then sends it. So that sender doesn't know which one gets decrypted at the other end. At the other end, out of K0 and K1, only one of them he will be able to do. He will not be able to decrypt both. For instance, he cannot get both M0 and M1 at his end. Had he sent C for C equal to 0, B equal to G power B, had he sent G power B, the receiver will be able to decrypt only E0. Had he sent A B power G, he will be able to decrypt only E1. The other one, he will not be able to decrypt. That means he can get only what he wants and nothing more. And at the other end, though he is sending all the information, he will not know which one was chosen by him. That's why it is called the oblivious transfer. Nobody knows what has been selected there. Yeah, yeah. To them, I'm just here to explain.
Common key is being selected by the receiver. That's the whole.
Yeah, because the receiver chooses which information it wants. So whether it wants M0 or M1. So C is chosen by receiver. But that C should not be revealed to the sender. Well, that is the goal of the obligation. Thank you, everyone.
strategies to get to a common goal. So now in most of the games, allocation of resources is very important. Even in our day-to-day lives and the government, what it does, it tries to allocate resources as efficiently as possible to maximize the productivity of the country or state or whatever. So in any situation, optimizing that is very important. So today we will discuss a very important strategy and algorithm related to that. Okay. Before going further, you would have obviously come across this game called Minecraft. Minecraft is a game in which you collect resources, utilize them to build more resources, etc. But there's a small catch when you're doing that. There is something called an inventory where you store all your resources. The inventory space is obviously limited. Just as practical usage, it's limited to a certain size of slots. Here, let's call it K slots. And then whenever you keep collecting new resources, you keep adding it to the inventory and removing them to make new things and all sorts of things. So you would obviously try to optimize. Being lazy is one of the main assumptions of computer science, I would say. So you would want to optimize that because you're lazy. Now what do? You would try to swap out the things from the inventory as efficiently as possible so that you would want to make the least number of swaps. However, in traditional algorithms, uh, one second. In traditional algorithms, we just deal with the fact that data is given to us. We process the data and produce some output. But there is a certain practicality in nature which does not give us the entire amount of data at the first. So what we are left with is that we have to make certain decisions in real time that would affect our output or optimality of the algorithm. So these decision-making strategies are known as online algorithms, which are a very wide range of algorithms which deal with data being processed on the fly. So a certain relation to computer science from the previous problem is known as the phasing problem. Phasing refers to loading data into the faster memory. Obviously, as you know, computer memory is arranged in a pyramid-like way, where the fast and expensive memory is of a relatively smaller size than the slow and cheaper memory. So you would want to minimize the use of the slower memory and you would want to load most of your data into the fast memory. Now, how do you do that? Can you correlate that this is the exact same problem as the Minecraft one? And dealing with page faults, which are when you can't access your required memory in the topmost section of the memory, they're very difficult and expensive to handle. So what do we do? Before we move forward, let's discuss how do we even check the optimality of an algorithm that we don't know the end product of. The online algorithms in such a way that they need to be compared with something to measure their optimality. Here we assume something called an adversary. Adversary can be thought of like a god who knows the future beforehand. Suppose he knows it, and being God, he will obviously make the most optimal term. So he will describe how each page fault is handled, or which term he will elect some part of the memory and all that. Now we can only compare algorithm as a subsection to the adversary's algorithm. So we define something called the competitive ratio of an online algorithm. It is an algorithm is basically called K competitive if it satisfies this inequality. The cost for the online algorithm is bounded by K times the cost for the adversary algorithm plus some constant factor. Obviously, this K should be independent of the size of the input or whatever to be called competitive. Now, before we move forward, we need to describe, we can model the exact same situation in the form of a game and use some game theoretic concepts as well. Obviously, this adversary algorithm works in a worst, we try to calculate such that it is the worst case possible for us. So it's basically that the adversary is trying to play a game with us in which he tries to maximize our competitive ratio and we try to minimize it. So it's basically a two-player game. Certain strategies like minimax theorem, cloning and all that can be improved in our decision making. Before we move forward, let's discuss some of the adversary algorithms which are the offline optimal algorithms as well. Mohan will continue for that.
So, mm, yeah. So, as Siddharth said, that our idea is to check the competitiveness of an online algorithm with respect to an offline one. So first we will imagine how does an offline algorithm perform. So what does it mean by offline? It means it knows everything. consider this sequence of page requests, and here the entire sequence is known beforehand. Mind it, these are the distinct page numbers. So when an algorithm or the adversary knows the entire page sequence, what would be its course of action? That we are going to see over here. Now consider the fast memory size to be of 3 slot, and then we see that at first it's empty. Let's consider it to be empty. Now page 3 is requested. Obviously it isn't in the fast memory, so it will upload it. Now 2 is requested, it will upload that. 1 is requested, it will upload that. So we have incurred 3 page faults over here. Now when 0 is requested, we see that the fast memory is full. So it has to evict one of these pages and upload page number 0. But which page to evict? That is the question. But our adversary knows the entire sequence. So it will look at this fast memory and check which of these pages is called at the last. Page number 3 is called just immediately after, 2 is again called, but 1 is called very late. So it is somehow better to evict 1 and upload 0. It does exactly that. Now when 3 or 2 is requested, it's already in the fast memory, so it doesn't have a problem. It moves on, does that. Now 4 is requested. Now when 4 is requested, again the same thing, same analogy occurs. It checks these 3 pages, checks out which is called at the last, evicts that page and uploads the required page for the user to use. So this algorithm, that offline algorithm, is known as the longest forward distance or LFD algorithm. Now it inputs this page request, and ultimately for this request sequence, we see that the total number of page faults incurred is 7, including the initial first 3, 4 other page faults are incurred. Now this is offline, which means it knew the entire request sequence. But in case of real life, we don't know what the user is going to request next time. So when it is requesting case number 3 over here, it doesn't know immediately 2 will be requested, or then 1, or then 0. That is the problem we are going to deal with in the online case. I'll move on to the next page, where we can theoretically prove that with respect to any other demand paging algorithm, this LFT algorithm performs the best in case of offline. It is the optimal algorithm. Now, for those who are interested, I have written down the theoretical proof over here, but I'll go over the general idea. The general idea is if we're considering an offline algorithm, any random algorithm as ALG, and we are considering algorithm star to be the LFD one at the ith step. That is the ith step. What it does is it checks the longest forward distance and evicts that page. Then we can see that with respect to then what the general idea is. Now, if the algorithm star is incurring a page fault, that means any other algorithm would have incurred a page fault beforehand, because the page that was evicted was at the longest forward distance. So any other algorithm would have evicted a page before that. And thus it can be bounded to show that the LFD algorithm is the best in case of an offline set. Yeah. So now we would like to generalize the problem with respect to the online setting by the HK generalization. Here we are parameterizing the fast memory of both the offline and the online algorithm. So what we are doing is we are comparing the performance of an online algorithm which has a size k compared to an offline algorithm which has a fast memory size of size h. So we are basically parameterizing the fast memories of the two cases so we can compare the competitiveness of both. This generalization is known as the HK generalization. Now we want to look at other algorithms that can solve the online problem. And the first thing that computer scientists looked at was deterministic algorithm. So one that I'd like to discuss over here is least frequently used. That is, at one particular instance, say over here, you know up till this much. And you have to make a decision over here that what you want to evict. For example, when 3 pages is requested, you don't know the rest of the request sequence. So 3 is inserted into the fast memory, then 2, then 1. And then and there, you are trying to make a decision about which page to evict. That is based on the least frequently used algorithm. That is, the page that has been requested the least is evicted. But unfortunately, we see that this performs very bad for a particular request sequence, which I've presented over here. Imagine this request sequence. So when page number 4 is requested, the fast memory is full, and each of these pages have been requested twice before. So you can remove any of them and input page 4. But now the problem arises that when 5 is requested, page 4 is the least frequently used. Now, obviously, the request sequence doesn't know this. It checks with its algorithm, edits page 4, inputs 5. And we are doomed. Because now, when 4 is requested, 5 is the least frequently used. It edits 5, inputs 4, and it goes on and on and on. So we see that least frequently used algorithm cannot be bounded with respect to offline algorithm. And it performs very poorly. So we must repeat it. Huh? Least frequent. After a couple of times. Yeah. It becomes least frequent, then get evicted. Yes, but we can repeat this sequence anyhow, right? So what Siddharth said, that we want to bind the competitiveness or we want to show the competitiveness of an algorithm. So we check a particular sequence that performs the worst for the online algorithm that we are trying to compute and performs the best for the offline algorithm. So
this question was about keeping track of history.
Right.
Right. Once 4 is evicted,
Yes.
you're looking only at the frequencies of the ones that are existing in your
Yes, you can't keep track of that. You can't keep track of when are ending.
the historic. That was his.
Yes.
If you keep track of that, then 3 would become least frequent.
At some point. Yeah.
No, because 4 has come in and gone out several times.
They can't keep.
After a while, 4 would have been evicted more.
Yeah.
But then we don't keep that way the information.
Right. It keep track of only the ones which are stored.
That are in the
Yes, correct. That is the reason why it is a kind of memoryless and it is working only on the current configuration of the. So although 4 was evicted several times in the past, when the third time 4 is inserted, it will still count 1 and not 2 which are there for 3 and.
Yeah, but that is the strategy we are focusing on. We're just demonstrating how that's. Yeah.
Yeah. Yes. It counts the number of. Yeah. Yeah. So, yes. And we will see an alternative to this. That is the first in, first out. Yes. So, first in, first out deterministic algorithm is basically considers the fast memory to be a list. It encodes the page which is requested if it incurs a page fault to the top and evicts the one at the bottom. But now we see an interesting anomaly in this case. So intuitively, if we have a larger fast memory size, we expect the number of page faults incurred to be less. But we are going to see something different over here. In this case, I'm considering one particular request sequence, which is this. Again, I'm repeating that each number indicates a distinct page. So initially 3 to 1 as it does. Now when 0 is requested, what do you guess? 3 would be evicted, 0 would be inserted. That's what it does. Again, when 3 and 2 are respected, unfortunately we have evicted 3 before. So 3 needs to be inserted again and 2 is evicted. And it goes on and on. So when we continue this request sequence in that particular order, we finally find out that the total number of page faults that we have incurred is 9. You can do this exercise at home with any particular sequence. But this is special because now we have increased the fast memory size to be of size 4. So we expect less number of page faults to occur. But if we do it with respect to the same page request sequence, we see that the number of page faults incurred is 10. And this anomaly is known as Velody's anomaly, which we see in this deterministic algorithm. Now, it can be shown mathematically that any algorithm that faces Velody's anomaly is suboptimal. So, scientists started looking for more answers and they came up with something called marking algorithms. I have shown here that the total page fault incurred is 10. You can check it. And yeah, so scientists came up with a different class of algorithms and that was called as marking algorithms. And before that, I'll introduce a concept called as phase partitions. So this again is a page request sequence. And we are considering the page size to be, the fast memory size to be 4. Now we are partitioning this request on a particular definition. I've written down the definitions over here. You can check it. Basically, what we are doing is we are ensuring that each phase has 4 distinct page requests. Check page 4 is basically the fast memory size. So basically, k distinct page requests what we are checking. For example, for phase 1, 5, 2, 5, 12, and 4 are the distinct page. Now, when the next new page request or distinct page request comes up, it's belonging to the next phase. The phase interval starts from the second of the first phase, ends with the first distinct page request of the second phase. That is a one particular phase interval. Now, what marking algorithm class does is it marks every page on the fast memory with a particular bit. It does a marking. And at the beginning of a phase, when it is doing that page request sequence, it unmarks all of them. And then when a page is requested, it marks. So algorithm works in a way such that a page which is particularly marked is never evicted out of the cluster. Now, yeah, I have shown the page interval, yeah. So this algorithm can be proved to be k by k minus h plus 1 competitive, that is k competitive. And I'll give you the idea of the proof. That is, consider the execution over one phase interval. So in one particular phase interval, we'll see how the adversary is performed. Adversary, you might remember, is the one who knows it all, who knows the entire phase request. We want to check that this phase adversary can perform. So if the adversary is really lucky, since it knows it all, what you will do? If you enter these few page requests, if you put these A pages in that particular slot it already has. Now, no, wait, I missed something. So we're comparing performance. The adversary has a slot memory of size h. That was HK generalization. And the online algorithm that we are comparing it with has a fast memory of size k. So the best case that the adversary would perform is it already has the distinct pages in the fast memory. So it doesn't incur page fault for those particular h minus 1 pages that was already there. But in one particular phase, there are k distinct page requests. So the least number of page faults that it can incur is k minus h minus 1. Yes? Okay. So the least number of page faults that the adversary would incur is k minus h minus 1, that is k minus h plus 1. So what is the maximum number of page requests that online algorithm can do? Is if it unfortunately doesn't have any of the k requests in the fast movement. So the worst case scenario is k for the online adversary and for online algorithm, and for offline it is k minus h minus 1. So this way we can prove there are more bits and bits inside there, but it is k by k minus h plus 1 competitive. Now, two examples of such marking algorithms are LRU and clock. Now, these two least recently used. It can be shown that these two are marking algorithms indeed, and LRU in practicality performs better than first in first out, though both are k competitive. It can be seen over a larger cache size. And now the question is, since it is k competitive, so now scientists started asking the question, computer scientists, as they always have, is can we do better? And this question will be answered by my friend. Okay. So now we are lagging behind on time. I'll try to pick up pace. See, we've makes the that means you can't really do the lab if the algorithm makes some basis. You can't really provide what the basis is. And then gives us something of new. New ways to learn. So let's move what you can do with this algorithms and create a
So, database online algorithm can replace the default organized algorithm. So, this is like easily put. You if they actually really needs to enter it, always which in the course. This is in the consumer. And since the everything is dependent, the release of the workers and the so now, you know, let's go. So, think we get into games, like, the insurance, it's getting different, the promise to algorithm, is to match the first of algorithm for the because the very well, the insurance become given away an offline algorithm, and the maximum of it you also know. Like, for each signal, the range something like that doing different algorithms. For this instance, so it's found cities of us that like information is the purpose. So consider cities where to create and then want to create. Now I'm also using the text in this literature. From the page, it's really that is the monthly elections still is not. So it's not fast about them, don't make any person. So what I'm saying here, the community is to get so the company will do it in the so it's so each one like like so is one person meeting. So it means it's the family is singular but we do. So we can try to read different for the way. I'm myself. So now I'm saying we're not going to the kind of movement to see my thing. So I'm starting we consider the person and we are not considering the maybe focus was easy. And because it's really indication. And that is really big one. And then, so these really focus we need to not touch. That is that's a good one we can do. And then service next emotion. So we can do in that case is we can start in the cases then you are really to then the data inclusive address is one. Then since we all have single then in that person. In that case, then basically and everyone else is in the so that's a bit of nice because single is even a thing it's 1 3 5 2 6 and you have that safe and the beginning is a really great idea. So when you put a line and then you have that safe and change your so 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 everyone having a system. series. The one that is is one if the primary increases and the wire level of onions. The other onions is the unit reverse groups. So the next thing one is the first one this time so the segments no, this is what I think this is rotating the page to so is not spaces and minus because I'm not so you know that the amount page you know the not the so not page is and so and then this is different. The see this is the news samples. And then there's the consumption anything else the vendor minus this is so then I this analysis shows that this so now, for the next one, Rania Sundar, I'm going to say that this is the best suitable. So the best solar is used. Is created. So it's a difference between it's best and usually best considered because the entries are honest, but the questions are then best was so instead of using random in that case, they bring like the they are the principles and the students. You can there's anything in the school, you can design this and then this is so yes. So that means the instrument cost. Therefore, goes to the police open person. The reason for the fair argument is very simple. Just the only know the advantage was given. So that's the second problem. And this can be very much universal education. So it was in the learning proposition. So we now see how dynamic algorithms help us in improving the performance by orders of magnitude. It went from linear to logarithmic. It's an exponential increase. So there are many such randomized algorithms which help us, but they're bounded by a certain ratio as well. Certain applications of this problem are using weights, like the variants basically, which are the weighted filtering algorithms in which everything a certain page has a certain cost associated with it and then it is placed in your memory and so on. So those also you can do in the same way. They are also bounded by a competitive ratio of logarithm of k. In that case, it is have to take into account of the weight while listing a certain page. And competitive analysis is also performed in the same way. So concluding the presentation, we've shown how online algorithms are useful and real-world scenarios to model these, and the essence of randomization in improving performance by orders of magnitude and making optimal decisions at every point of time. These algorithms are obviously used in various things like cloud computing, database design, and every high-speed machine needs to take care of all these requests at real-time input. So that's it from our side. Thank you so much.
mentioned, point about unified genetics in stock markets to simply known as the genetic algorithm using the concept of natural selection in markets. You can point to the same more about the two monkeys for looking at this presentation.
Yeah, please. There is a guarantee that the audience won't be here.
Am I audible in class?
No, not
Hello, hello, hello.
yes. Is it coming up from the mic?
No, let it be.
In a random walk on Wall Street, Martin Luther King famously suggested that a blind man is by experts. It brings the title from monkeys to markets, harnessing genetic algorithms for financial forecasting. So, while the notion of this whole financial forecasting seems very challenging, its correlation with Darwin's theory of natural selection is very interesting and hence led to the discovery of what are today known as
Genetic algorithms are very useful in optimizing complex problems and they can explore a vast market landscape. So, let's see what exactly genetic algorithms are. Genetic algorithms consist of search, adaptation, and optimization techniques that are based on Darwin's principle of natural selection, or they use biological operators like crossover, mutation, and inversion. Now, these are placed in a class of algorithms called evolutionary algorithms. In 1950, Alan Turing was the first person to ever propose a learning machine that was based on the principle of evolution. However, GAs were popularized in the 1970s through the work of John Holland and his fixed-length simple binary algorithm. And a lot of us are not very familiar with biology, so we will be explaining this in algorithmic terms. First, we represent chromosomes as strings, genes as the bits of string, and alleles as the values of the value of the gene.
yeah. So this is a 5 point tutorial for GS for dummies. So I'll be explaining the first 3 points. So let's say we have a bunch of solutions with us, and out of those solutions, we want to have a solution which is optimal out of every one. So my first step includes initialization. So initialization is basically selecting a small population from your whole solution set and then applying various methods to that population. And the population is selected in a very random manner so that the diversity of every solution is maintained and we don't lose any optimal solution while in the process. So the next step includes fitness evaluation. Fitness evaluation is basically assigning a positive number to every member of the population selected. The fitness evaluation is needed to see if we want to maximize or minimize the fitness function to yield an optimal solution. So it is a map that basically maps your phenotype of this chromosome to a positive variable. In selection, selection still means selecting things from a population who will be reduced to produce higher efficiency. We use two methods for selection, one to median selection, to limit selection. For median selection, we basically have a very child selection for median is directly proportional to the fitness syndrome. So I have an interval of say 2 to 3, which is mostly considered as a higher fitness in this selection set. So I'll assign, let's say, the D part of this pie chart is interval of 23. So whenever I spin my remote wheel, there is a higher chance of selecting a parent from set D than other sets. So it generally maintains the diversity of population being robust in fitness functions also. Also, there is this tournament selection where you take two or more than two people and basically prepare the fitness selection. The one who wins in the one who player all the minimum fitness function. Because
is selected. So let's say out of 2 and 7, the 2 has higher fitness function than 7. 2 goes forward and participates in reproduction.
Now that we've selected our parents, let us apply reproduction to the population. And let's reproduce the population. We do this using genetic operators. Genetic operators are basically used so that we can explore the widest possible range of solutions so that we can find the most optimal solution. The first genetic operator we use is crossover. Crossover is basically a form of artificial mating. It can be done in many different ways. Screen which we are using here is the 1.2 screen. So first, we select two strings which will be current strings. We take a random line from this space. When we select the children, we take the left half of the first string, we have the second string to form one string. And then we take the left half of the second string and right half of the first string, form second string. So it shows that we have two children distinct from identified patterns. Now, the process is a very relation with identity naturally eliminating. And which algorithm we use is mutation. The mutation basically we take the parent string, we take the parent string and pick a value in that string and we choose the value of the string. Mutation is because of a very low probability we can ensure that there is free massive diversity in the population. Now that we have reproduced the population, seed production keeps going on for many generations. Every combination criteria is here. Now, this is the combination criteria is ideal for maximum number of generations have been achieved, or that the GDP of the population converges, which means that the individuals with the population have the exact same strengths and the exact same chromosomes.
So after we make any algorithm, this question we ask for ourselves is why does this algorithm work? What's the purpose of this? So this algorithm basically works on the principle of schema theorem, which is also known as fundamental theorem of genetic algorithms, which says that genetic algorithms can not simply work with many pairs in cells. The idea is if I have one chromosome, it ensures that chromosomes very similar to these chromosomes are all consuming one consuming only that chromosome. How is that? So string of chromosomes, the binary string has ones and zeros in it. I don't know about any unity function which depends on only 3 out of 5 bits I have in the chromosome. So if you assumes are not just don't care symbol, which is also known as schema. So every chromosome having those two bits is considered if I consider that don't care bunch. So this implicit parallelism combined with the fact that bad schemata are removed using the genetic operators as crossover and mutation is the central advantage over other problem solving techniques that GA is given.
Now, why exactly do we use GAs in finance? That's a big question we have. First is that they are payoff driven because they are motivated by the result and the outcome. They are motivated in nature and they offer parameter optimization. Let me give you a real example. Suppose we are interested in buying and selling a stock. We want to optimize our profits. We want to maximize our profits. So, GA means what exactly should we buy the stock or sell the stock? Student concepts are maximized. The G's also provide a large variety of constraints, which are usually harder to implement in traditional methods, and they're also very adaptable and customizable. They can be used to solve a large variety of problems. Now let's come to the actual main algorithm, which is genetic programming on FGP1. Genetic programming is basically an extension of GA. When in GS, chromosomes had a fixed length string representation, but in GPs, they have towards different tree structures which have a variable length and a dynamic representation. These representations are called programs. And the GP operators like dictionary and mutation are modified from those gene to work on keys instead of strings. With the selection procedures and combination criteria, most same ones that we used in GS.
where we use trees instead of spoons for GP, we'll have to make a setup for working of genetic programming. So first we have a set of functions whose arity is greater than zero. That is, that take arguments. Number of arguments are greater than zero. It might be possible that they have greater than one arguments also. Also, I have set of terminals which are which correspond to the leaves of those trees, the programs we make, and they act as inputs to my functions or as an output of my tree. And we have fitness measure. Fitness measure is basically a function that takes the program, that takes the whole program as an input and assigns a positive number to it. And we have some parameters for controlling the. This basically includes the maximum what I can make a maximum count of that I can make, because let's say I have many functions, say 5 functions and 7 functions. I can make a very skewed tree with a very high, with a very big height, which won't be necessary for my algorithm. And termination criteria, which mostly resembles benefits, which is if the maximum number of generations have been, or the phenotype of every program converges. This method of every program I have is safe and I cannot change it.
Now let us look at the key representations of the programs and services thinking about generating precision trees. We can say that these trees with its evidence like section set and the independent nodes consideration. This is a very good example of a GPT right here. This can be read in order progression. So you can see this is not C on C and H on 92. So basically we use GPT because they can store a very wide range of key structures and we can get very continuously in our creator developer. We use many customizable and we can adapt many different performance metrics into these variables.
So this is the pseudocode for the main algorithm. So it explains the step. So I'll first partition my whole data into training data and testing data. If I am running an algorithm, I have to know if my solution is optimal or not. I'll do that using the testing data, using the testing databases. So the first step is initialize population from POP. Population is basically taking some set of chromosomes out of the whole solution set I have and evaluating fitness measure for each of the chromosome I have taken. Then the chromosome corresponds to the species. And then I now know which.
Now, when we selected our credits, we start reproducing like in GS. For reproduction, we use selection procedures told in GS for selecting the credits, and then we apply operators like crossover and mutation with their respective probabilities. And what is this way? This presents suppose we have correct individuals in our population, and the probability of crossover is in PC. So we try to ascertain the untimed species of the individuals. Now, suppose again for mutation, the probability of mutation is clear. So we apply mutation to untimed clear number of the individuals. Now, this loop keeps repeating till the termination criteria is where we can ensure that after each iteration, the next generation has a will less than the previous generation. So that keeps going on till the termination criteria, which I hope we have repeated that enough times for you to remember that by now. After it is done, we apply a custom identity testing, which basically means that we give the individual benefits only the one as the now, how exactly are these GDPs used in industries? If we basically make buyer sell decision in reaction to mistakes, we either need to reduce them or solution. So we use explanations as in functions in the GD. Now, so this is an example of very basic example that we give one here. Functional branch with a select is basically which one's in utility rules in labs. So for example, suppose the value of an indicator is less than 2,000 dependent x. We drive stop and otherwise we sell the stop. So the then and the else branches correspond to via cell decisions and the conditional branch is via the selection.
against these various parameters. Now, these parameters can be customized based on the user's network behavior. The actually integration takes place in critical practice. When customers mostly have these two parent generators, customers can separate each of the generators and we swap them. Then we get the children generator, right? As engineers, both of the children are distinct from organizing levels and proceeding with the major operating unit. Next, for mutation, the really one parent, we select only something freely event and then we delete the something to replace it with another browsing the generated software. So that's basically how the operators have changed one and changes.
So we might be wondering what a fitness function is on this word for like 5 times now. So for financial forecasting, the fitness function is basically how accurate I am with my predictions. So in most cases, my fitness function is represented as rate of correctness, which is the number of correct predictions I made divided by the total number of predictions I made. So in some cases, I either need more than one parameter optimized. So my fitness function can have more than one criteria. But in most cases, it should be more than one for each of them. In I'm making an algorithm to make it simple, make it convenient to inducing a very complex fitness function. So mostly methods of like least multiple method and something are used to maximize the functions in more than one criteria. In financial forecasting, yes, higher prediction accuracy is desirable. So, solution with highest fitness function is the one we want after it. And we have to make certain trade-offs with the rate of correctness. We cannot be we cannot make rate of correctness as optimized and very close to one. Like if every prediction I make is accurate, that won't happen. So that will happen if you consider the population. If you take the population sub exactly as same as the number of students you have, but that would take a high computational time. So I don't think that exactly what that is the thing we want. And yeah. Now we have ordinal forecasts. So ordinal forecasts are forecasts that use the most accurately predicted data till date. So let's say till time t, I have some series of data. Let's say I'll represent it by y, and y of t represents the value of y at time t. So what I want is the best forecast of the most likely y of t plus h value, given an information set till time t. That would just be the expectation of y of t percent given I have some information set at time t. The information set till time t consists of y values I have up until time t. Let's say for an example, I have a weekly closing data of a stock market in my given y. So in time t, I have the data still I have my weekly closing prices. So I use that data to you can estimate what would be my weekly closing in table stage, what is day, and that would be my best forecast can give. Yeah. So let's say I have P1 to PM discrete forecasting categories. Forecasting strategies basically are, if I take an example, let's say that bullish, bearish, bullish. So P1 to PM will represent what my forecasting category is. As the number of categories, obviously. And I have, let's say, up until 20, I already have 12 predictions with me. So my goal is to combine these predictions to form a prediction EFT as a function of these predictions. And my target is that the average case of EFT will work better than the best case of all predictions I have until now. Okay. And obviously my EFT will belong to P1 to PM because these are the only forecasting categories I have. And mind you that EFT is a function of E1 to EN. So it can take values, it can take any value from E1 to EN given my initial conditions, which I give in my terminals.
Now let's look at the case study how this applied in the real world. Using a compound method, the statement is selected field to physics paper by generally for the University of Other Finished in 2000. First, we take 103 data cases
which consists of 9 expert predictions. These would be the input terminals that we use. And the actual market state. Predictions by the 9 experts would be of 4 categories. One is bullish, which means the index rises by over 1.3% in the next week. Bearish, which means the index falls by over 1.3% in the next week, which means basically you're not really getting money. You're losing money. Sluggish means the index is neither bullish nor bearish. And uncertain, which means that expert refuses to make a prediction which rarely ever happens.
Yeah. So, as I said earlier, I have 9 predictions that were given by 9 expert predictions. So, and I have a set of 1, 2, 3, 4. That is bullish, bearish, sluggish, and conservative. And I have to make a function out of these 9 predictions such that this belongs to my forecasting categories and hope that the average accuracy of EFT outperforms the best accuracy of all of them, all of E1, E2 up until EF. Yeah, so this is the data we took from the thesis. So they divided the whole 103 data set into 3 different categories, and whenever they ran one category, they used the other 2 as their test cases. So my objective is to find GDTs that have an accurate prediction. Input terminals were my 9 predictions that expert predictions. The prediction terminals were 0, 1, 2. He has removed uncertain because it had very less probability of happening. My function set includes if then else and or not, greater than, less than, and equal to. If then else, as we told, why if then else is a compulsory condition for most GPTs, and or not basically combines 2 terminals and gives you a less than equal to, less than, greater than, equal to, makes you take a decision on buy and selling a stock. So fitness function, as I said, is the rate of correctness, the number of predictions. You can see here that the crossover rate is 0.9, while the mutation rate is 0.01, which is very less than the crossover rate, suggesting that the operator mutation acts as a background process, while crossover is the main process happening in the population. And the termination criteria was the same. Yeah, the selection strategy was the tournament selection of size 4. Size 4 basically means we took 4 chromosomes and the one with the highest fitness first. And these were the results the thesis had. So the average accuracy of all the 3 data were this, and the mean accuracy turned out to be 0.5039. That means almost half of the predictions I make will be accurate. And this is a table comparing my accuracy with other traditional methods like extension, multinomial logic, linear programming. And as you can see, genetic programming outperforms all other 3 methodologies. Hence, it is a better solution to financial forecasting. These were the references we took. We took our aspect from this video talk. Thank you.
Yes. Questions from the audience?
Yeah.
Yeah. Yeah. So, so do you think that, I mean, yes, so in some cases, this may be better than, let's say, that algorithms for optimization like NP or, some other power optimization methods. But in what cases is this better, and why do you think this better? Why is it better?
I mean, only reason I could find it to be better because if it was, let's say, a robust solution for X percentage, it was very random for, let's say, 100 minus X percent. Every method we implement while doing genetic operators and stuff is very random in its own way. So, maintains the diversity up until the end. So,
if you show it, so if on an algorithm, it looks a little bit like, let's say, some sort of descent, on some space.
yeah, it is a linearly decreasing.
Right. So, in some sense, it is a greedy algorithm, right?
Yeah,
So
in
when-
some way. But
People think it has a So, I mean, it will not work. If there are keys, you know it will not.
I don't think we found a case where it does not work. I mean, it is not a greedy algorithm.
It's failing to pick fitness properties and other things.
My algorithm is designed in such a way that it only picks the population which has a high fitness function after every iteration.
It will find some maximum.
Yeah, there might exist more than one optimal solutions. It only has to find one.
I see.
Yeah.
But you know, when it will fail to find the best, I mean, not just the optimal sub. What I mean is like, then find a maximum sub.
Yeah,
But-
that's what was written in the fitness function thing. We have to make a trade-off for this. Either you will increase your fitness function or you will miss the maximum optimal solution.
See, when there are several maxima, we might get stuck in the local maxima.
Yeah.
Right? That can generally happen. In that case, one can do some perturbation, which is also a standard technique in these class of algorithms. So you are stuck anywhere. Search for certain neighborhood for any possible improvement. And that is one technique, but in general, this gives probably because of the ascendancy you experience because of the selection.
Your target is always to give less computation and get a good output. If you want to have a global maxima, you will give as much computation as a brute force approach. So no point of doing that.
So if the fitness function is, if it induces a total ordering on your positive configurations,
Yes.
then I think we are guaranteed to go to some level maximum.
Yeah.
Right. And otherwise, you'll depend on random perturbations, which I don't know.
No. Because monotonicity may not be there inherently. So you cannot have one function that is going to have monotonicity and keeps keeping up to the maximum because of the fluctuations and variety of ups and downs. You have at best it is going to reach local maxima. And in the financial prediction and marketing, the context itself is in such a small range that there will, I mean, you expect to have only one maxima or one peak. That's a small peak. If it is a very large one, there could be several one. So this succeeds in that because the local maximas are typically one or in the range in which investigations are. But if you are trying to say what is going to be the prediction for the next 6 months, I don't think anything would, I mean, no one will be able to do that because you don't have either a meaningful data nor convergence to maxims.
There's one more problem that if you, hit some set of fixed points, then you will just not be able to proceed. Let's say all of your, all the child population will have the same fitness as the parent in some particular iteration.
Yeah, that then termination criteria hits and it's lost.
Yeah, then you'll have terminate.
Oh, if you look at the table, the percentage is 0.56, while experts have done 0.4 or something like that, this has done 0.5. Still, the fieldworks and other things are expected and experienced and so on. Can you show them? Yeah.
0.3. So 3 options you are finding. Then correct?
Yeah.
Totally random scheme, right? So there are the beginning between 0.3.
Yeah. Point five.
0.5.
0.503.
So the prediction accuracy will be 0.5 for a totally random algorithm.
Yes.
But then everything else is so bad that you can invert it. What also the alien programming chooses, I inverted the decision, I'm better off. Read it with which?
No, but the point is it's about prediction, right? So we.
No, then I invert the prediction, I'm better off. Is that what it means? That's what I'm
No. This is enormous. It gives you better than the expert.
By inversion does mean instead of getting the best, we get the worst and this
That's fine. Taking a prediction. Will it be 0.3 or 0.5 according to your metric? I think it's 0.3, right? I think 3 prediction, 3 possibilities. P functions 3. And maybe choosing one of them at random.
And
No, if you make a completely random prediction.
Yeah, but this shows that is better than experts. See, experts have made a prediction and then on-field verification is done when the actuals are happening in future. The agreement percentage was shown. Now that we have a frozen data, experts have taken data up to some point and made prediction, and their successive SE is shown here. On the same data, if you put in genetic algorithm, what is its outcome and how much it makes advantage over the. So this analysis is done on the frozen data. Generally, it is shown to be good, but then obviously 0.5 shows that even this one is
Kind of.
yeah, it's like a coin toss, right? So that is the
Yeah, that's what I have known. I think maybe it's
fluctuation in the stock market is something that is absolutely crazy. Just even that it is giving better than point toss itself is encouraged. Okay.
Right. So, as previously, I said, quite an ingenious idea. Right. So now, from our keys to markets and now to markets, algorithms. Do you know what technology our present encryptions rely on? RS, right? High compilation of extremely large numbers. So now I'm handing over the mic to Aditya and Om Prakash, who would be dealing with one such algorithm, which probably can break our present encryption techniques quite efficiently. So yeah, handing over the mic.
This okay.
Hello, I'm moving at the back. Okay. So, hello everyone. Today me and Om are going to present about quantum computation and Shor's algorithm. So, as said by us, Shor's algorithm is what is potentially going to break the RSA encryption, which relies on the fact that you can't prime factorize a very large number. But I'll be motivating the idea of quantum computing and how it's helpful and going to be very beneficial to us. So, there's a brief history into quantum computation. So quantum physics actually came into around 1900s beginning when the classical physics was very problematic and started creating many problems in microscopic realm. So this is where quantum physics came in and started to solve the problems. Then later, Turing came up with the computation formalism, which had a mathematical definition of how algorithms should be defined in around 1930s. But it took another 60 years or so for Feynman to formally give what a quantum computer should be and how it will work. Even today, it's in its very experimental stage, and Google is also having, and IBM has a quantum computer with almost 70 qubits. But the algorithms have been continuously researched since 1990s because people know about the potential a quantum computer could have. So, what exactly can a quantum computer achieve which a classical computer cannot? Basically, both computers solve the same set of problems. There are no such problems which a classical computer cannot solve and a quantum computer can. It's just that a classical computer will take more time and a quantum computer can take less time. So here by computation, we mean that there exists an algorithm to produce the correct output, provided you are given infinite memory and infinite time. But we all know that this is not what is practical. There's no computer that has infinite memory or nobody has either infinite time. So we need some kind of speed up mechanism where we are able to solve the problems faster. And this is where quantum computers come to help. However, there's only a certain class of problems which a quantum computer can accelerate. Not every problem can be accelerated by a quantum computer, and not every problem, and some few problems which can be accelerated by a quantum computer. This is called quantum supremacy, and people are trying to achieve quantum supremacy by around 2030s. Uh, yeah, so sorry about that. So, how exactly does a quantum computer achieve quantum exponential acceleration? The simple answer to this is qubits. Qubits is just another formally name given to quantum bits. So, how is a qubit different from a standard classical bit? And how can we understand it very intuitively without going into the physics and math rigor behind it? Let's think about a simple coin. A coin has both a heads and a tail side. Can we simply map these heads to the state of 0 of a classical bit and tails to the state of 1 of a classical bit? Yes, that works out very well. So anytime you keep a coin on the table, it lies either on its one side. Now, just think about tossing the coin and while it's in air, you're photographing it. So it would be like one of the given pictures. So at any given orientation, if I give you a particular snapshot of that coin, you will be able to somehow intuitively come up with a probability of whether it will land on a heads or a tail side. You will never be sure about whether it will land on a heads or a tails, but you will have probabilities for both heads and tails. So this fact of having probabilities and not exact values for outcomes is what helps a qubit works faster classical bit. So this is just a schematic diagram. A classical bit takes either 0 or 1, but not both at the same time. But a qubit has probabilities associated with the state 0 and state 1. Since they are wave functions and on going into the deeper of quantum physics, that is why this notation of Dirac notation is given, but we don't need to worry about that today. So what exactly is the advantage if a qubit can exist on both states simultaneously? So thinking about one classical bit and one qubit. Since a classical bit can take only one state at a time, if we have an algorithm that performs a function on any such classical bit, we first have to perform the function on the first state 0 and then the state 1, which implies we can simply do a simple count of two computations here. But since the qubit has information about both zeros and ones inherently within it, it's not completely evident, or it's wrong to say that it's both 0 and 1 at the same time, but there is some amount of information concealed about 0 and 1 within it. So when we perform a single function on a qubit, what happens is that it performs the function simultaneously on both states 0 and 1. So we see that it performs just one computation for both states 0 and 1 simultaneously. To understand the exact advantage of using qubits, we need to extend the idea to multiple qubits. So we come back to a standard coin analogy and toss multiple coins and take a picture. So we'll get a picture of multiple states and we can still associate probabilities with each coin. Now, I think everybody over here is just familiar with the simple probabilistic ideas of independent events and tossing of coins. So if you toss multiple coins and if each coin is associated with the probability of heads and tails, how can you write the probability function of the total outcome? Let's just go into a simple example of two coins. Let P1 be the probability of heads coming on the first coin and P2 of the heads on the second coin. It's very simple to say that it's probability P1, P2 of heads. It's P1 and 1 minus P2 of heads and tails. It's 1 minus P1 into P2 for tails and heads and 1 minus P1 into 1 minus P2 for tails and tails. It's very simple from independence of events. What we need to observe here is that now we have probabilities associated for every single outcome of tossing two coins. There are four outcomes and we have simultaneous probabilities for all four outcomes. Whereas if we were to just use two classical bits, we would have either one of these four states, just one of these four states. So this is the interpretation of the net result. So if we now to perform a computation in these three classical bits and two qubits, we see that we need four computations for just two classical bits, whereas we only need two computations. On extending this idea to n classical bits and n qubits, we see that we need 2 power n computations for using a classical computer, whereas just linear time for a quantum computer. This is the exponential speed up that we're talking about using a quantum computer. So this is just a very simple diagram of when exponential is going to become very worse compared to a linear state. So now a very simple quick question can come into everybody's mind. Why can't we just replace all classical bits with qubits and have the same computers? We just replace our CPUs with some quantum machinery and have the same algorithms as what we all study ever since. The problem with this is that quantum physics has something additional known as wave collapse. So wave collapse is basically when you measure some particular form of outcome, the entire wave function collapses into that outcome. So to intuitively give an idea to this is that our same example of tossing coins was that we had probabilities. But the moment we allow the coin fall or rest on the table or we allow it to fall on our hands or something, we immediately reduce ourselves to just one possible outcome. We no longer have probabilities because we literally have seen what the outcome is, and our probability of the other outcome is zero. The same analogy can be extended to even n qubits, whereas when we toss n coins and we see that there is a particular sequence of heads, tails, there's no probability associated even with any other outcome. So we see that all the 2 power n states will collapse into one state the moment we make a measurement. Then how exactly do we make an advantage out of it? Because this seems like we are just adding a lot of machinery, but yet to get the same time advantage as a classical computer. This is where, okay, so this is just a pictorial idea about how a tossing coin will fall onto one side, and we see that we have reduced our sample space of outcomes to just one. So now we need to deal with how to make different algorithms in such a way that we actually get a benefit out of it. And this is done using entanglement. So to picturize entanglement, instead of a coin, let's take a dice. So the dice, even when taken a snapshot in air, still has probability associated for every number that's possible. So if I show you a picture of a dice in air, you can write a probability function for every number that's going to fall in it. But the additional advantage you have here is a constraint about its geometrical construction. So if I tell you that the number 1 is observed after it has fallen, you can immediately tell me like a magic trick that 6 is on the other side. Why? Because the construction is that the sum of numbers on the opposite sides is 7. So this means that you have interlinked two possible outcomes in such a way that the moment you gain information about one side, you immediately know what is on the other side without even making a measurement. So this was just entangling two possible outcomes. When we are dealing with a huge number of outcomes, we can entangle multiple results, and the same principle of entanglement as well is used in Shor's algorithm. So you can see how Shor's algorithm is going to use entanglement to deal with the outcome. So this is just a very animated picture of how entanglement is, where qubits are portrayed as spheres when you go into the subatomic level. So this is just they're interlinking them. So the moment you measure one of the other qubit immediately becomes obvious as what its outcome may be. So let's only continue on Shor's algorithm and show you how we exactly factorize the product of two prime numbers into its factors. Okay, so I'll be talking about Shor's algorithm. What is Shor's algorithm? Shor's algorithm will take a very big number, which is of the form of product of two prime numbers, and it will give us the factors that are the two prime numbers. Shor's algorithm runs in polynomial type. Polynomial in the sense of number of bits needed to represent the very big number. And it uses the ideas of modular arithmetic, quantum parallelism, and quantum Fourier transform. We will give an intuitive understanding of each idea in upcoming slides. So here is the brief overview of the algorithm. So at first we need a number which is a product of two prime numbers, and we make a random guess x. Now we need to check if GCD of x with n is equals to 1. This is most likely the case because n only has two prime numbers, and if we take some random number, it's not going to be one of the factors. So GCD of x and n will likely be 1. Now the third step is what Shor's algorithm actually does. So I'm thinking. In the third step, we perform the Shor's algorithm, and what it does is, given the number x and it finds a solution r which satisfies this inequality x raised to the power r is equals to more than uh, x raised to the power r more than equals 1. After we find that, now we know that x raised to the power r minus 1 must be divisible by n. And if r is even, then we can factorize x to the power r minus 1 as x to the power r by 2 minus 1 and x to the power r by 2 plus 1. Simply integrate identity h square minus b square. Given these two numbers, we have some information about the case of r, and we can extract the information by taking the GCD of n with respect to these two numbers, x to the power r by 2 minus 1 and plus 1. Yeah. Well, if it's so mentioned that the number r which Shor's algorithm gave us is odd, then we are in a bad luck. We have to start again. Even if it so happens that GCD of x and r by 2 minus 1 turns out to be the number itself, then we again have to start with some other random number x. So now we'll describe a result from number theory.
The result is very simple. The sequence x raised to the power p mod n is a periodic sequence. We define period as of the sequence r. R is the smallest positive number such that x raised to the power r mod n is equals to 1. We demonstrate this by taking example of x as 7 and n equals 15. So in this case, we see that the period is 4. 4 is the smallest number for which this holds. 0 is a trivial case, we don't take 0. Another important example is that all the numbers will appear after a period. So we must note that the period in this case is 4. Now, to this point, we have shown that the problem of factoring the number is equivalent to finding the period of the sequence, and we'll use solution algorithm to see how we can find this period. We'll be demonstrating Shor's algorithm by factoring 15, and we start with a random case 7. So here's some terminology. A register is a set of qubits. For working of Shor's algorithm, we need two sets of register. One of them will call as left register and other one will call as right register. The requirement is that the left register must be big enough to hold the number which we are trying to factor. So here we are factoring 15 can be represented in 4 bits. We is fine. Unit register must be big enough to store the values of model, which is to the power of model. So those numbers will be smaller than n, so we can take it of 4 bits, 4 qubits. And another convention is that when we say measurement is like 6, we actually mean the measurement is 110, which means the qubits are in the state 1, 1 and 0. However, we'll use that notation because it's much convenient to write. So now assume that somehow using some black box we get the superposition. What is the superposition? In every state we have left register and a right register. The left register will contain all the values from 0 to 51. We took a 5-bit register, so it has all the values from 0 to 51. Then corresponding right register has the value 7 raised to the left register mod 50. So we can't just basically get this superposition. Actually, we have to pass through multiple quantum gates. But it does not affect the working of Shor's algorithm. It is time complexity and other stuff, but we will not look into the quantum circuits and everything. We'll just understand the mathematics. No. Okay. So I have expanded the superposition here. We can easily see the periodicity in this one also. Now suppose that if I notice that the right register in every state only takes 4 values, 1, 7, 4 or 13. If I perform a measurement on the right register, let's say the value came out to be 0. So that was our old superposition and it collapsed to this. This is actually entanglement reaction. Related to a measured system. When the system collapsed to a state in which every relation has so this is the entanglement. And this is actually contains information of the field because 7 will always return after 8 number steps. This superposition actually has some information on W. If you extract that information, you use something called inverse Fourier transform. This is the inverse Fourier. So, like as people, we have 3 clocks. One clock rotates with the frequency 1 Hz and 2 Hz and 3 Hz. But I'm not telling which clock rotates at which Hz. Okay. So you want to find out which clock has 1 Hz frequency. One thing you can do is you take 3 pieces of paper and start updating that paper at 1 Hz frequency. Every time you update, you draw a line along the hour hand of the respective clocks. So the clock with 1 Hz frequency, you will observe the clock again at the same phase if you update at the synchronous rate. So this is what Fourier transform does. If you give it a periodic sequence like the angle of the clocks, it will give back this is actually a summation of roots of unity in a complex step. So we'll see the mathematical formula in the next segment. The main idea of inverse Fourier transform is that it converts a periodic sequence to a new sequence which is encoding the period. In this case, the summations of the uh, uh, roots of unity. So this is the inverse quantum Fourier transform. It is the same idea. Here the state A is the state which we are applying and n is the total number of all possible states. we'll see a result which will help us to simplify this inverse Fourier transform operation. So this is a very elementary result. This is just a summation, and summation has some linear term Pn plus k into a constant c and n. All we need to note at this point is that this summation is only non-zero if c is a multiple of n over p. That's all we need to note from this. So on each of the states, this question which you collapse, all of the numbers is separated by a period, and we'll apply the inverse Fourier transform, and it will become a double summation because we are applying on a superposition. Now, this is a double summation, but actually in quantum computers, integrating can be useless. You don't have to actually move over and simulate. All this space represent as one superposition. So we can write this summation as a terminal part. In that context, which I was talking about in the previous slides, is actually this statement 1, 2, so on, so on. So what we saw in the result that if we sum around the column, only those two will be non-zero whose C value is the multiple of n over period. So if we sum n is 32 and period is 4, so we must expect multiples of 8 in this case. This is our final superposition. We have multiples of 8, 0, 8, 16, 24. These are only multiples between 0 and 31. So our final state had 0, 8, 16, and 24 as the state in the superposition. 0 is that trivial case. Other than that, all the states has some information in the period. They are multiplication of 1 over p period. So what we can do is we make a measurement. Let's say the measurement value is m. So we must be a multiple of n over p. It's not inverse Fourier transform. P must be a multiple of n over small n. We can take this in a classical computer and we can start from n equals 1 and we can keep checking which value of p will give 7 to the power p mod 15 equals 1. This operation is very cheap other than going reverse. So yeah, so the p value which any classical computer will give is 4 in this case. And the once we get the 4 numbers, we see that the p is even. In this case, p is equals to 4. Then the factor can just be found by doing the GCD, this and this. So we have applied the GCD. We got the factors 5 and 3. There is a result which guarantees that the we will will get this factor successfully with probability, which is even greater than 60%, but we won't prove that result. That's the short algorithm. Any questions?
In my understanding, the power of the qubits is that there is a probability associated to it.
Yeah.
So you have a bit, it can be a qubit or a classical bit, and then you have operations, and then you make a measurement of some sort.
Yeah.
You get what the output is. So the operations part is anyways a black box.
Yeah.
For qubits, you still, if you make an operation on a qubit, you still have to make a measurement.
Yeah.
You have to go to the final score. So what is the need of having qubits if you can, in another way, take a normal classical bit and have the functions and the operators that you're applying to be probabilistic. So I'm just changing the black box. You have a qubit, you apply deterministic functions, and then you get a measurement which is because of a wave pattern. Why is that needed? Why can't we just have a bit, make probabilistic functions instead of making superposition or basis? Why can't you have probabilistic functions, and then in the end you still get one state as your answer? So won't that be equivalent? Why is the need of any superposition?
So exactly the problem is that to do something probabilistic on a classical computer is not that easy. Say if you have to do a random number generator, even using Python or anything, it still has an underlying algorithm that does it. It's not exactly 100% probabilistic. But using a quantum computer, you get almost 100% probabilistic ideas because it's a wave. Ultimately, it's a wave and it's 100% probabilistic. And the more advantage you want to see is that what a qubit does is that it allows you to do things in parallel simultaneously. It's basically like telling instead of doing one task on one computer, let's say you have 50 different computers and you do all of them parallelly. But since you don't want to use that extent of resource, You can manage that parallelism just in one computer by using qubits. Yeah. Ultimately, your computation is done using quantum parallelism, but the pre-processing and the post-processing is finally done using classical, because once you measure a result, it's ultimately classical.
The exponential parallelism is reducing the things in the time scale. The sequential machines have got a Turing bottleneck, and therefore NP hardness, NP completeness, exponential complexity, and other things are. In cryptography, we use the hardness to prove the security problem. You say that certain things are unbreakable or you cannot decrypt and other things by saying that there is a hard problem. If it is possible for you to decrypt, then that hard problem can be solved in polynomial time. So what we have taken is factoring. Factoring is not solvable in, not known that it is solvable in polynomial time. So far, there is no polynomial time algorithm there. Do we have a lower bound on that complexity? No. We don't know whether it is NP complete or not. We don't know whether it is a polynomial time solvable. And cryptography is security is depending on such number theoretic functions. As of now, the security properties that are given as a guarantee in cryptography are all based on these problems, number theoretic reference problems, which are kind of hard. Okay. Now, the hardness is measured in clock cycles. The moment if I have a quantum computer can break that clock cycle or bring in exponential parallelism, then the whole thing boils down to polynomial. Hence, all our assumptions on cryptography doesn't hold good anymore. You can't solve it in polynomial time, doesn't hold. Right? Which means it is possible for you to crack all the encryption, government standards, and you name it. Anything that is around can all be broken, provided if you have a full-fledged quantum computer, works on it, and harness that exponential parallels. This is a model. As of now, even the lab models are achieving to some extent, but a lot of research work is going on. But the current status is that the actual parallelism achievable with the physical system that are designed are all very limited. However, we have a theory which says if you have sufficient amount of parallelism enabled, assuming that one such system is available, you're all going and all crypto will come to an end is perfectly sure. It's a landmark result. It has shaken the world and such an exciting thing. Right? As you are saying, the exponential parallelism is the key winner. In principle, we can definitely, as you have said, have a black box or a complete, some simulated version of that implemented on. But then that question is going to take exponential, right? Because it has to do one after another, everything that has to be done. The function is to be evaluated for the result through the regular steps that are done in your online membership. It has to go through the clock cycle. That's the broad point. The technical details are there. When you go deep into the model and other things, you can see various aspects.
I just had a comment. There are two things that work out here very well. So, like sir said, if you wanted to write a function to apply this probabilistically, you also loop over all the states.
Yeah.
And in an entangled state, all you have to do is apply it once.
Yes.
And magically everything is fixed. The second thing that works here is measurement is a very special thing for state. So you're querying the state and it collapses into one. Now what happens when you query the state is that you get one number here and immediately the preimage collapses to only the preimage of this x star that, or you got some f of x star and the preimage immediately collapses from the whole set to an x star. You're referring to entanglement. Yes, entanglement is what helps you do this. But this collapse is very important. And the moment you get this collapse, you're working on a subgroup. So the math here is group theory, and it's a much more gentle.
It's a yeah. It's like yeah. Questions? Any other questions? Yeah. Okay, so if there are no other questions, let us thank the audience. I have one announcement to make. there is a minor change.
Yeah.
It looks like we seem to have said the lunch is at 1 o'clock, not at 12:30. So it's arriving. So we have the can we shift the talk now? The next talk, is the speakers available? Immediately after lunch, whatever was the first talk, where is that? First vanished. What students the next there is some minor communication gap. I don't know where.
Shamsi, who are going to present competency.
So first, your take on latest right? Do you have a pointer of it? Oh, yeah.
Very good.
So, our second is more now. It's important. Yes, most of you wouldn't have prerequisites. So, I mean, the UG first year. So, I would like go through the notations once. Right, yeah. So, your A would be the probability of occurrence of an event A, an event in a sample space, and E of X would be expectation of a random variable, and I of A would be indicator, which means it returns one if an element is an event A, and P of G. I mean, these are like very simple properties of graphs, which I assume most of you are familiar with. V of G would be the set of vertices, and E of G would be the edges, and this is uh, an unordered pair of unordered pair containing I, j and ordered pair, and this is required because at one point we would require some clean combinatorial notation. So we would go from unordered pair to an ordered pair, and di would be the degree of a vertex, right? And which is like which counts the number of edges incident with a vertex vi and yeah. And what are randomized algorithms? These are algorithms that make random choices during its execution. So that's realized by the fact that the running time is a probability distribution or the output is a probability distribution. And the paradigm that we are concerned with is would be the Monte Carlo randomized algorithms. And this would be a basic example of how something like that would be realized. The problem is you have a line of being consistent of 2 1 lines. You're supposed to find a number native on the median, right? Greater than or equal to the median. There's a trivial algorithm in 5 steps. But there is a constant of one randomized algorithm. It goes like this, like you pick randomly 100 points. And the question is what it means to be random is something very different because that's a pretty big question. But assuming you can do something like that, you pick something 100 number points and rate it the maximum and my claim is this is supposed to work. But uh, I'm working. Okay, yeah, it does. So the probability of winning would be very extremely less as you can see. Like, so this is just very basic independence. I mean, I'm assuming you know what it means to be independent and so on. So this is what I was talking about. This paradigm of randomized algorithms. Like, this is named after a casino in Monaco, and these are sort of algorithms. These are not they are not expected to always return a correct value, but they have the probability of error can be made as small as possible, as you can see. And this is like my favorite, personal favorite, and you're supposed to estimate an integral of a continuous function on 0 1. I mean, if you can do it for 0 1, then you can do it for any compact interval. And, uh, and without resorting to analytical methods or numerical approximations. And it's often the case that you cannot resort to analytical methods. And the idea is to use random numbers. Uh, right, and my claim is this would be an estimator of your integral, and all you do is you sample. Um, this is called the Monte Carlo symbol. You sample random points from the interval 0 1, and I mean, assuming you can do something like that. And my claim is this would be an estimator, and but that would require you to know uh, Chepsays and the reason the claim is this works, but but that would require you to know the Chepsays inequality and the reclaim of large numbers of like this can be skipped and for an n sufficiently large this works and can be approximated to any arbitrary degree of accuracy. Yeah.
Okay, so max cut is a problem of significant combinatorial interest. It's a very simple problem to describe on graphs, but to sort of motivate for you guys, I thought of taking like a real world example. So Ganesh is a school student. More importantly, he's an artist. He sees an opportunity to start fights in his classroom by selectively inviting a bunch of students for his upcoming birthday party. So he thinks that to maximize the likelihood of a fight breaking out, he should invite people such that there are the maximum number of rivalries amongst the group that he selects and the rest of the classroom. So how do we help them? Well, we will graph of course by modeling each student in the classroom as a vertex and letting an edge join two vertices whenever there has been a fight or a rivalry between two of the students. We sort of translate this problem about helping Ganesh into this is Ganesh's class by the way, into mascot. So given a graph, in instance of the term, we will find something vertices x that maximizes the number of edges between x and y. So this is Ganesh's class.
this is the maximum thing. So he should invite either his from 0 and 1 or 2 through 9. So one popular heuristic when solving such complex optimization problems is to go greedy. If you're going greedy, let's look at this, greedy algorithm where you start with, arbitrarily place a vertex in A and let B be empty and iteratively go through all vertices and maximize your local gain. But it's not right because in the case of Ganesha's game, you're getting only 9 edges from the greedy strategy, but maximum 16 edges. But you might be wondering, then why am I showing this to you? Well, the thing is, the message algorithm gives you a lower bound on the number of registers in terms of the number of registers. It's not in the management stuff, it's in terms of the number of registers. So you can get a guarantee that this algorithm always cuts half of the registers. And since maximum must have more than this, the maximum must always cut at least half the registers. Yeah, guaranteed to produce a cut more than half the registers. And that's significant because that means all instances of maximum more than half of the edges. So, I'll be discussing 0.878 approximation algorithm in the next few slides, but why is it significant? Why should you be interested? Why should you care? Well, according to a conjecture from the unique games conjecture, it's actually everything. You can't go better than 0.878. And even if the unique games conjecture is not, which most people believe it is, if P is not equal to NP, you can't, which is that class of problems is not equal to another class, you can do better than 0.9 for 1. So 0.87 is pretty good to what we consider to be best. So let's see how you can achieve this using a Monte-Carlo algorithm. So consider this expression. It might seem convoluted, but just stick with me for a while. Yes, yeah. So consider this expression where we're summing up over the edges this quadratic, this polynomial 1 minus x by x of j divided by 2, where all x's are either 1 or negative 1. So this sort of domain where all points are 1 or negative 1, you can think of it as points of the vertices of a hypercube, where a hypercube is a generalization of a cube in high dimensions. So my claim is that if for anything, I can give you a vector in point on a hypercube, vertex on a hypercube, such that C value of that point will give you the number of times in that particular set. So consider the points in the vector in the point generated by this function, where whenever a vertex is in a set, you assign 1 to that particular index and negative 1 whenever that is it. So to make it clearer, consider this example. So here we know 0 and 1 are part of the set. So if you consider the whole function of it, then be 1, 1 because 0 and 1 are in the set, and negative 1 for others because they are. And that evaluate on the C evaluating this function with this x gives C, which is precisely the number of edges that are between in the count 0, 1, 2, 3, 4, 5, 9. So yeah, the proof of this is simple, right? So if x y is equal to x, both of them are either plus 1 or minus 1, so the product is definitely 1. So this will be 1 is 0. And if they are not, only happens when they both belong to the same set. That means we shouldn't count their contribution to the company. So if they are unequal, that means they belong to different sets. X is included in that, and that evaluates to 1. 1 minus 1 divided by 2, that's 1. So yeah, similarly, since this is sum of all edges, and we are only adding 1 for every edge that's we are only counting the number of edges that actually. So you can show that any assignment of ones and negative ones also corresponds to a cut, a partition. But I guess that's pretty trivial. You can just go the other way around. So finding max cut is the same as finding the maximum of this expression C over all points of, over all vertices of this hypercube. So why don't we just do that? Well, there are 2 to the power n points. It's a discrete domain and it's very difficult. This would be a solved problem by now. So why didn't we try and relax it into a continuous domain so that we can take advantages, offered by calculus, continuity. So consider this instance, serial instance, where you have n plus 1 vectors instead of n plus 1 booleans, not booleans, n plus 1 integers, and you replace the product with the dot product. And the condition is that all of these vectors must have unit norms. That's about it. And then of course, is that the maximum of the serials must be greater than or equal to maximum C. The simple way to prove it is you take a solution to C, that is y1, y2, yn, and then consider the allied solution, E times y1, E times y2, where E is a unit vector. And then we know that if you have two vectors, E1, E2, then it's equal to the normal, product of two integers y1, y2. Since E1, E2 would be 0, and we know the by the connected input having is taken. So you can show that the serialized is greater than or equal to max by mapping any solution to C to a solution serialized. So maximizing serialized. So this is a bit of algebra. You don't have to trust me on this. That you can simplify it into this form. That you can simplify it into this form where we sort of make it into an equation that's written completely by matrices, where X is a matrix which whose ijth entry is a dot product of vectors X1 and X3, where D is a matrix whose diagonal entries are the degree, it's called the degree matrix, and A is a matrix where the ijth entry is one if and only there's an edge between I and J. This is the adjacency matrix. But yeah, you don't need to trust me. But I guess the slide should be made publicly available so you can go through it. An interesting fact about the matrix X is that it can always be decomposed into a matrix like this, when the rows of B and the vectors themselves. So you can represent X as a product of B in the B resource. So this is pretty powerful because it tells us that this is especially coming from matrix, but a positive semi-definite matrix, which has always its eigenvalue and non-negative. And if you look at the diagonal entries, those who correspond to the norm of the vectors x naught, xi. So what this tells us is that we can, instead of maximizing all those vectors which are difficult, and there are a lot of vectors that correspond to the same value, same input, you can just maximize it over semi-definite matrices which have diagonal entries 1. And fortunately for us, this set is convex, and serialized is linear. And maximizing linear functions over convex domains is something that a lot of work has been going into for a long time. So there are methods that are particularly integral point functions that approximate the maximum within a fraction epsilon in polynomial time, where the degree of the order of the polynomial would depend on 1 over epsilon. But for the rest of the analysis, I'll be assuming that we can get an exact solution. There will be a couple of epsilons if you actually consider this, but I'm disregarding that. So this is where, this existed before Gummins and Williamson's proposed their novel learning schema. This is actually what changed the game. So what they did was they found the solution from the SDB solver. Then they found vectors that corresponds to this solution. They generated some random variables. And then they put this procedure where they effectively put it into sets if they satisfy this dot product criterion. So let's see where this works, right? This seems completely, why would they do that? Well, a fact is, if you normalize the random variables in random variables, what you find is that the random variable you get is uniformly distributed over the hypersphere. This is a fact. We've provided a proof. You can go through it in the slides. And another fact is if you have a finite number of indicator variables and you sum over and you take the expectation of this, that's just the sum of their probabilities. That's also falls from probability for expectation. So I'm going to assume these two as fast. So the probability of an edge being cut, if an edge exists, is the same as the probability of Vi and Vj not being in A together. So exactly one of Vi and Vj have to be in A. So if you consider the arbitrary vectors Vi and Vj and the plane passing through them, you need to find the probability that exactly one of them is in A. So you can, when you're doing the analysis, you can actually let go of R perpendicular because R perpendicular dot Vi would be 0, R perpendicular dot Vj would also be 0. So you only have to focus on the component of R along the plane Vi Vj, which is, I'm going to call it V parallel, R parallel, sorry. So if you think about it like that, if R parallel is in this blue region, Vi dot R would be greater than 0, so it would be included in A. Otherwise, if it's in the zone region, it will be smaller than 0, it wouldn't be included in A. And you can do a similar analysis for Vj. And then we can we see that in the red plus blue is perfect. So what we get is that in these purple regions, exactly one of them is in A. Exactly one of what see Va and Vj are in A if R parallel is in this purple region. And now the probability that R parallel is in this purple region, well, it's just the area of this purple region divided by the area of the circle, which is 2 theta divided by 2 pi, which is theta by pi. So now we get that, the expectation of the number of edges is equal to this term. The summation of theta some ij over all unordered constants over pi. And this seems completely random, but this is really on paper. So what we find is that this function theta over 1 minus cosine theta, it has its minimum 1.38 over the domain 0 pi. This is the graph. This is about the point. It's about 130 degrees. Yeah, and also since since originally we assumed that the vectors were unit vectors, you can reframe cosine theta as the dot product between VA and VJ. So we can get it of the form theorem ij over pi greater than 1.38 pi into 1 minus cosine theta into cosine theta ij, which is same as 0.49 into 1 minus v sub I dot v sub j. And using that in our sum, you get this. And now we're converting this unordered pair into an ordered pair since we're dealing with not pairs that don't have any sense of damage. When you're converting it, ij, unordered set ij would correspond to two ordered pairs, ij and j. So you can just, do the sum by just dividing it by 2. So that's zero last, and that's max C, and we showed that that's greater than max cut. So it's a 0.878 max cut approximation. So let's consider this graph. This is a wheel graph, popularly known as W9. This is its solid this is max cut and solid max cut. So we can count 1, 2, 3. For all of these right vertices, there are 3 of them. So there are 12 vertices that are compact. So the SDP solution to the wheel graph would be something like this. It would generate a vector like this, V1, V3, V5, V7 at an angle of 105 degrees. These are the 150 degree angle, and these are the 105 degree angle. And now I ran the rounding scheme, and what I got was like the algorithm of the cut value is 11.24, optimal is 20, since it's about 0.9 for the max. So this is like a full question to end with. Can like analyzing the SDP, I think of a reason why the randomized rounding will always return the right answer for Ganesh's graph. Will always return the one with 16 edges. Yeah.
Yeah, the questions are extremely difficult result and mathematically deep, and they have taken phenomenal amount of pains to make it accessible. Kind of every expression and the intuition behind that expression, geometry, taking it across. The amount of effort taken by the team, it's really phenomenal. It's a very deep result, one of the deep results. And Gomans has given full course on approximation algorithm in MIT. You can see his lecture notes on approximation algorithm and course details there. Really advanced course. Approximation algorithms, they are offered in various places, in various levels. So the MIT course is one of the famous ones. And his results, his course talks almost every day like a seminar type of course. Every day one breakthrough result from stock talks or some advanced results even covered. It's very difficult to follow this course material, but then if you take patience and then follow it up, you will have an extremely rich experience, knowledge, competence. In approximation algorithms, algorithms will all be very simple. It's their analysis that will be mathematically very deep, very challenging, And that's what it is shown. But then they have shown more or less all the points that have been in this fashion. The connection between C and the very awkward looking expression that actually it carries so much of information. Exactly the Prof. It's got all of them there. Well done. So let us appreciate all the speakers. And now, just one announcement. The lunch is ready. The lunch is configured in the following manner. There are two counters. The salad section is
in 1 to 2 minutes, so please kindly be seated and just pause your acquaintances with your hosting and your host.
Chaitin.
Yes.
So when
Take up a snacks and then from that. You go ahead. Huh? I'll come back in 2 minutes.
So welcome back everyone from lunch. Before we move on to the next presentation, I would like to ask you a question. How many of you are beginner programmers? Good programmers. There is so much about high level programming languages. Unfortunately, the next presentation entitled Register Allocation using Chaitin is not finally available. Shows how much effort goes on behind the scenes in making these high level languages reality. One such algorithm, introduced by Revolution, specifically used during register allocation for compiler design.
Pointer.
So let's first try and understand what register allocation actually is. In compilation, where we want to go from a high level language, like let's say from C to machine code, there are many steps which are involved in compilation. Once it's step, the compiler goes from a high level language like C to an intermediate representation. Then, in an intermediate representation, usually it's a lower level of abstraction than a high level language, but it's higher than machine code, and it's usually platform independent. One feature is that in C and Hybrid languages, we can use infinite variables. Even in intermediate representations, you have to use infinite dependencies, which are substitutes for these variables. And the library usually does most of its optimizations from this step onwards. So I mean, but as we know, a CPU only has finite memory processors. And for the CPU to do any operations, or it can only do operations on data stored on these finite memory processors. So any data you have stored in main memory, you have to load it into the registers for the computation to happen. I mean, one naive way to do this would be to just load before an instruction, whatever data is required to execute that, you can just load that into a register and then follow up with the computation. The issue is that you don't really fast efficiently as possible. Since loading the main memory is much more expensive than having data stored in your registers or in cache. See, one automatic to make your data to make your program as efficient as possible, you're incentivized to make as little nodes as possible. So we want to store data in registers as much as possible. Let's now understand how we can represent this problem. So figures have some instructions, procedure defined a sequence of instructions. It's kind of understanding how we go about solving this problem. So we need some sort of model to simplify and streamline our thinking. So what we can do is for each temporary being used in the instructions, we define something in the live range. A live range is defined as the times as the time step when a temporary is being defined up to the time step where it is once being used. You can see that each instruction has two different time steps. One is for evaluating the values, and the second time step is for storing the value in the actual register. Now, with this, we can make some inferences. Now, if we have, let's say, three registers on a CPU, we can simultaneously use those registers to assign to different live ranges. As you can see, in a single time, only maximum three registers, three temporaries are interconnected. But this way doesn't give us a proper procedure how to give the assignment of registers. So we'll model this problem again into something called the register independence graph. In this graph, every node is corresponding to a temporary, and there is an edge between two nodes if their line ranges interfere. That is, same time step, if they both align at the same time, then there is an edge corresponding between them. Now this problem can be reduced to one of graph theory, where for if let's say we have k resistors, we assign k distinct units to the node one graph such that no connected vertices have the same value. This will ensure that we assign resistors such that there is no interference between them. Now, actually, before Chaitin, these comparisons to the graph problem have been made for this resistor integration problem, but there was no actual implementation utilizing this fund. So what Chaitin did was in, I think in 1981, he formally rigorously proved and reduced the resistor allocation problem with the graph theory problem, and came up with a wonderful algorithm which allowed us to solve this problem. So the graph theory problem is incomplete. So the Shocking bricks heuristic is only an approximation. It's a way we can solve it in polynomial time. So it uses an insight to draw the common graph. Essentially, if we have a graph which is k commutable, and if we remove an edge from it which has less than k neighbors, the graph we get upon its removal is also k commutable. So it uses this to successively remove such edges and then to color it from like a bottom up perspective. So, but what if there are vertices with degree greater than k or equal to k? Then you have to do something from like as I mentioned before, the trivial way to solve the way to load data from the memory to the registers before each instruction. So it's basically going back to them. And let's explain that in more detail later on. So this is essentially the solution. Let's start understanding with an example. Essentially, as I mentioned, you remove the nodes specifically with degree less than k, and you push it onto the stack. And if you run to a point where you can only find edges like that, then you mark it as a potential fill candidate, but you still push it onto the stack, and then you pick out the edges successively, and you can use them. So understand this with an example. So just a small connection where proper by vertices, I mean that they associated with the vertex, and when you put the vertex, they will square down k neighbors. You say the example. This is the same register open this now, which we prove from the manual instruction set. So we see that here we have some vertices with degree less than k. T6 we can see has a degree of 0. Now we have chosen k equals 3, which means we are working with three distinct real resistors available in the CPU. So first of all, we can pop T6 onto the stack. Then we can see T5 has a degree less than k again, so we can pop T5. T4 is a degree of 2, we can again pop T4. Now you see that T4 from this to this, we can see that Q2 also we reduce the delay. So now we can actually put it into this way. Initially, it may seem that it is integrating multiple registers. If on we this reducing the timing to smaller, we can see that we can possibly achieve delay. We will see how the delay happens later. So we continue pumping the loops, and we can see we have reached an ending now. Now, if you recall that Chaitin makes Jerusalem, it we sometimes experiment that if the branch is uh, a branch is clearable if a name is the branch G dash obtained by removing a node with degree less than k is also clearable. Now, what we have done is successfully removed vertices with degree less than k and achieved the node color. Then empty node is clearable, which is what the original node is also clearable. Even when we are trying to open the theory, you start by open these vertices out the sum in the same way pillars. You can recollect filters. If it is not negative connection, you can assign any layer. That's really playing familiar. Each statement T2, we see that T2 is only T3. So we can't say green. We can say any other color. So we go with blue. Then again we put T1. T1 is independent, both T2 and T3. So we use the sign another color, which will change the color. Again we put T4. T4 you can see you can tell T2 and T1. But it doesn't include T3, which means we can reuse the color green. And as we proceed in this very manner, we try to manage uh, the pop-up nodes such that they do not interfere with the other plans. And after the circuit is active, we can see that we have achieved a rate with this graph. And now what we can do is in the instruction code, instead of these temporaries, we can assign corresponding resistance. You can see an example of the resistor indication in the graph. For the blue color, we can use R1. For the blue, we have used R2. And for the green color, we have used R3. You can see that the same instruction set was reduced to something which uses indicator resistance, when avoiding any interference between the line ranges of same color. Which means we were able to achieve resistor limitation quite easily. However, as I mentioned before, what if we run into a problem where we have C's with degree greater than 3? In this case, we can see that there are, of course, simultaneous differences. So obviously, we wouldn't be able to assign registers at this time instead. Let's see how the algorithm deals with this case. The corresponding register difference will figure is this. And as we can see, T3 has vertices greater than has degree greater than 3. So let's see what happens. So we just pop T6 and T5. Here we run into a problem where we wouldn't be able to put any more vertices. I mean, yeah, vertices. So we we choose to split the potential down there. First thing is when we topic outcome is found, is only potential and we continue with the execution. On the end of the empty with an empty graph, and we start off the convert procedure. So T4 obviously we can convert with one we want, and T3 we convert blue, and T2 can also be converted. But here you can see that T1 cannot be converted since T2 is comparing with posts of all the possible colors. So hence the so you have to take it using scalar. So in this case, uh, first of all, what is spinning? Where does it come from? Spinning means storing the values of the entity into memory instead of continuously storing it in a register because we need to utilize the register for some other purpose. In this language graph, you can see that the P1 temporary is being used in the first, third, and the fifth extension. It is not being used in the second and fourth extension. So, what we can do is to save T1 into memory, use it in further instructions, and load it there once it's needed. So, how can we do this? If we say it, before and after every instruction, it utilizes taking. So, before the instruction, we know from a memory location, and and I can choose this string in the memory location. First instruction defines table, then we store it. Then it is being used in T3 again, so we need to load it before the T3 instruction, and after using it in the third instruction, we store it back, and so on. Now you can see that the line range of table actually gets split into three distinct graphs. What we can do now is instead of assigning only a single category, we can distribute these line ranges into multiple categories. Let's give them names T7 and T8, and we have successfully split the line range. What this allows us to do is we can build another register graph, which can be potentially very more easily. So in this case, we can see that the has increased. Uh, I mean, as we can see, does this mean it can't be coming? Let's see what will happen. So we got T1 and then T6 and T5, and here we can see that we have four vertices with degree less than 3, so we can push either of them. So we continue doing that, and we can see that by the time we reach T3, its degree has reduced. So we're able to push it. And now we can move on to coloring it. So T3, we can trivially color it with whatever we want. And T2 with any color that's not green. And T8 can be colored since it's anything with only two vertices. And T7 can also be colored. And yeah, we will be able to find the coloring since we never reached this fill command. And we end up coloring it as shown. So let's see what is actually happening. Since we split the line range of T1 into two separate ranges, although the number of interferences with T3 has increased, none of these are simultaneous. We can see that the number of maximum simultaneous interference is still 3. So, which is why we're able to cover it. I mean, you might ask yourself, can there be a possibility that since we, in this case, we have this number of simultaneous interferences are decreased? We reach a stage where we can no longer find anything and and we wouldn't be able to find legitimate covering? Well, the answer is no. Because as I mentioned initially, the trivial way to solve this problem would be to put any data which is stored in memory into the register right before its execution and then to store it back into memory. Essentially, the spelling is just that. I mean, if we have one range which is causing a maximum interference greater than the number of registers we have, we're essentially just loading it from memory before each of the instructions and we're storing it down. So basically, going down to this case. We're guaranteed to always be able to find it in line. So let's try and understand what the time complexity would be. On single iteration, like we have no fillings, I mean, a single filling, it would be with B square, where B would be the number of vertices in the graph. This is because in each iteration, you're updating the graph when you push a vertex into the stack, and then you also find a vertex with degree less than 2 for the next step. So this is all the iteration, and you're doing it 3 times potentially. So the time complexity would be of B square. But in the case of splitting, we usually there are more optimizations done in the beginning with the lag ranges, so that the number of splits don't aren't too big. So usually it happens in polynomial time. Yeah, it is possible for it to take exponential time in some cases, but this is usually very rare. Now here we are only discussing a very simple case for registration. We will not deal with any branching code whatsoever. But uh, in actual use, this requires a lot of thoughtful thinking to to make sure that the program actually works perfectly on computation. We know this go into the details of this. We will discuss some little optimizations which we can make to improve this process usefully. The first thing is we can optimize the spell code insertion. So in the previous example, we inserted the spell code as in the form of restoring those locations. But if you see carefully, we need not store that a value which is anything useful zone. If a value is only being used for a unique device, we can simply go to user and consider the values to be contained within these instructions. We need not store it here because there is no change which is happening to that actual value. So we can omit these store instructions by limiting the language to these two instructions. This reduces unnecessary memory accesses and overall active users. Other heuristic helpings are, for example, when you want to choose a node to spell. For example, when performing the algorithm, you may encounter a state where no vertex has a degree less than k, but multiple vertices have degree greater than equals to k. So you need to determine which vertex exactly to spell so that your actual companion code is restricted to and also the register verification process also does not take too long. So the same general points to keep in mind is that we need to avoid spelling temporaries which are usually used because those temporaries will be if we spell them, they will be loaded and stored back into the memory iteratively, which is fine for the performance. And regarding the choosing of the temporary, in general, we should choose temporary with a high degree so that the line range can be split into maximum number of bits so that we have the best chance of proving by reducing the number of interferences. Another heuristic optimization can be made during the line splitting, where instead of splitting the line range, we're introducing storing new instructions for each use of a category. We can instead split the count of interference. These are some of the references in the original paper by Chaitin and others on register allocation by Eric, a later paper by him on some improvements using scaling and some new improvements by which utilize optimistic tuning and other heuristic approaches. We also took help of the Dragon book, which is infamously known, and we are also grateful for some lectures from these professors. Thank you.
State of questions. Any questions? Yeah, here, there is a question.
So the coloring or in the select or move the vertices, if we all have equal degrees, is it randomly put it as that or what? Yeah, so and the company has to make a decision regarding that. Now, this choosing spell coming is what we use. So there is actually in general use there is a cost function defined associated with each spell candidate, where you want to choose a node which minimizes the cost. So you opt the most optimal choice in order to spell. These involve various parameters based on the use case and stuff. So you can read into it in textbook and stuff. Not in school, but generally if it all degree is less than k itself. If there are four ones in circle or whatever it is, what is it random or what? Yes, you can choose random. You will always see the answer when you are able to compute every node while the degree is less than k. The Chaitin brings heuristic guarantees that. But actually, if you do some intelligent analysis, you may be able to achieve, develop some choosing strategy which optimizes the register allocation where they are distributed more equally. Any other question?
Okay, and this time I want to add more. Coloring problem is one of the hardest problems, optimization problem, but even approximation algorithms do not exist. Right? I mean, approximation of constant ratio. So there are various levels you can get close to the optimum solution. Ideally, is the constant ratio, the ratio between optimum solution and non-optimum solution. Yeah, if it is a very small ratio, it will be good. Okay. But sometimes log n ratio is acceptable, but not desirable. However, there are problems like set cover and other things you cannot get anything lower than log. And for covering, we just cannot get closer even these log factors also. So it's one of the very hard problems. And so what requires whenever you map certain problem to coloring problem, since you can't use even good approximate solution for it, you have to use very clever heuristics for it. The breakthrough result here is the kind of a clever heuristic that has been used rather than using an approximation. Okay, so that's a very interesting point of this. And that's why they made it work in practice. Though they modeled it through a very hard and nasty problem, the way in which it was practically dealt with is very interesting. So that's why generally the theory research is categorized into a few theoretical research and then applied research. Then there are pragmatics. Pragmatics mean these methods are practically useful, but then you may or may not be able to get a formal analysis in the proofs and other things for us. But in general, they will work uh, very well. The famous example is the linear programming repeat problem. The simplex method is so well known, and at the time when it was introduced, everybody knew that it is working very well. They don't know why it works well and then how well it works. Both of them they do not know, but then it took several years to understand even basic nature and the principles of. So there are several live and practical problems of this flavor. Okay, and that shows bridging the gap between theory and practice requires several interesting strategies, both generic as well as the hawk. Okay, so this is an interesting case study in that direction. That's thank you. Sorry.
Now that we are having our discussion on efficient register allocation with Chaitin's graph analysis algorithm, started to something different. Constant algorithm. So that uses graph theory and alternatives of interesting patterns in revealing connections that other techniques might miss. Please join me in entering knowledge into the more request to the school of functional explications.
So fine, I have done an analysis. We are going to present something question, which is question. This question. So, what maybe one maybe so this is a question. This now you have traditional synthesis in the means using an EMs. However, these methods are not generalizable. Since they are using the data is complex and many other assumptions. So for non-complex specific situations, or generalized solution of data rather that, you have no method to see situation using data. So now what are the implications I see? So you use streaming imports want to find instructions on this method, you use the triple. And bioinformatics, you see use symbols and then you identify groups of coexpress fields. And image segmentation, identifying the different segments of an image, the different kinds of an image. How is it use the triple C? They want to testing. So, okay, so traditional testing use its easy. We just go to sequence C, look at the future. So, these express yes. You go, you make these. Now you choose the random key, and the key is the image fixtures. And you randomly initialize functions. You form the clusters using these. Many people essentially these data points in the cluster and appear single points. And so on so on. So this eventually rewards this anyway and this functions doesn't this now you get this data is a this because the particular errors in this usage. So this is inverse history. Okay. Now you have many data streams, like so that's the graph and efficient.
So one is exploration of nodes, social contests, and technologies. Now, in efficiency nations, it's the nation's simulation of a belief wherein the initial element of the efficiency nations is just a way of knowledge. Nothing mentions the simple in region is the simple. The degree of the node is same as instead of the region and measures a move and just the way of knowledge, instead of the node. Now, someone got us to see them. Simple life is for the nations of people, and that resources that the news. Now, what we need is the people simple news to create difference. We have data, we create a graph representation. And for the graph representation, you need objects. So this government similarity news, the similarity nature. And so that's how it works. Because now let's say use description for this function is once, because we feel that I was because of the Western coordination. So when this is not the graph, like the graph with classing, which is simply actually the right people. The profile structure composition JSON was complete with database elements. We use these elements to check on the lower dimensional space. And then on the lower dimensional space, we have materials. So consider the image because it not use the ground streams. So now let's say the manifestation of data. So I have database CSA. So notices in the databases. When I just sources and so then it was in points. So if you can so you there is a PDS there. And then ways functions and the differentiate just simple and showing this function. When we use this one, the guidelines to now so this is an achievement. This is something that using anyway. This is something that one using aliens using aliens. It's how you use natural language system unification using the so my opinion is also saying because the same city. It's nice. Yes, so the image is saying this is you have before. Okay. Now you can graphic see. Unbalanced processing, balancing is really the minus these dimensions. And the minus dimensions. So this is the graphic processing. This is obviously true because the is as mass. Like yes, it's a single thing. This is all of its values. Because when it's the model is this is the main one, which is using the main ones. So we have those release. So if I improve the one in the matrix, so if I improve the one of the chances of using the benefits. So when those are usually information, when there is information, there is the resource. The senses of services is the information. Yes, and then this is it. Yes, how does the information so I think there is a musics. Never knowledge structure information. Knowledge structure information. So the meter is about the everyone will see. This is everyone will see this. And everyone is also the same identities. So actually, structure first, the level from the values. So first thing we do is we have to prove this analysis is the so okay. So we have this relation to level, which we know is what is if is in negative level, and we is the minus is this stays in the plus. Okay. And we are using simple concept, which is the definition. Since the family is just actually really is. This way, the family in the level is wants to develop emotions. Yeah. And then we see which is the goal of your care people of the comparison. Now, you need this solution. Now, if it's really so things is easy. So, if this side doesn't this is efficiency, then this side everything is zero and everything is efficient. Okay. Very easy. Okay. Yeah. So, let's issue. And what the initial issue is, we already have cases such that we need to notice the level of the data continuum. So, what that means is the vertices in this one and one will be represented continuum. The basis in the that's label, label to same when this is the problems. So we have two data variables. When we introduce the variables, we damages when you can see the secondary patient level, the factors reaching these results. And for many vertices, they will understand what is damages as is we can like basically is different sources related matters in the ones. So if we look at this we like element and this is really very indicative of each of the involves. So this we give the screen and this components still the involves. So I'm going to is what is this really is very very because we are in decomposition, switching decomposition. Finally, that the idea that this chemistry is serious and basically this is switching in the loss. And it's not single, which is actually the feeling is switching of the so okay. So anything of the other communication from the is not enough. There is some wisdom missing in it. We also positive competition limits share usually feedback is one similar otherwise in the units. Now this system is two pieces. Two pieces is not fixed here since this during values. So now progress is so now is the level space is the this is many different. Now this is so this the next is possible to do which is the best changing is so this is really using the mention of how easy it is to see the changing since it is really structure section is really very so, if changing is changing, this may put under processes. This is why speaking of changing, certain degree of changing isn't so changing represents and since now we know that this is change in this sensible is easy to say to really those things and it is not it's so feeling the mention in the body that must be release is consciously now, community generalize this to cake history. So, for cake history, we use the history, we use higher values. And the identity is specifically negative, different benefit of two pieces. And yes, there is a generalized case. We have a we replace this in lambda k label, we have an h k g, and then we have case into lambda. So the genetic system can convincingly install into different systems, then using the case source. Now, okay, so I'm going to example indicate personality chemistry represents what maximum easy to native matches next to school. Now, this is an example. And that was easy. Now, look at this. This can be seen actually to succeed even which is wonderful. This is a distinct from easily consumed programs. Now, look at the co-organism. I will do instance in four different ways. So, I don't know this, 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 this. So previously we really just make as customer first. Now you guys think that this is the person and this is the market. So is it belief in the name of question. And sanitization is the belief the number of the solutions of the this is not a scientist information at the moment. So
So now let's understand this problem in terms of graph cut problem. Now, as you have already learned that what is graph cut, and now how can we model this problem to graph cut problem? How can we model this problem to graph cut problem? That's if we are having a similarity matrix, if distances between 2 points is very far away, then similarity function will be small enough. And if we remove that particular edge, we are removing edge with minimum cost. So we are minimizing edges to be cut to two clusters. So in this way, we can model this problem to graph cut problem. Here, if we are using graph cut problem directly, we will get into a problem because some outliers will be there in data always. So graph problem generally put those outliers ahead, aside and give us the partition, but we don't want that. We want both of the cluster to have significant number of elements. That is, we want clusters to be kind of balanced. So we define that, and the problem is this, where we divided it by mode. Mode is number of vertices present in cluster A. Now, yes. If we use this particular equality, which we have already learned how to prove this, we can use this problem to this particular problem where we are what we are doing is we are minimizing this particular thing where y belongs to indicator vector of graph and subjected to that particular constraint. But now solving this problem is NPM, that is way too hard to solve for a computer. So we will reduce this problem to y belongs to R. We are using this y range from indicator vector to whole R. So after reducing this particular range, we will use rank quotient theorem for solving this. According to rank quotient theorem, this particular equation has a solution. Its minimum value is second smallest known negative eigenvalue and corresponding value of y is corresponding eigenvalue of that particular uh, value. Now, what is Rayleigh-Ritz theorem? So, first we define a constant Rayleigh quotient as this. Now, subjected to f, we want to minimize this particular thing where n is some constant. This will minimum value will be when this minimum value will be second smallest known eigenvalue of t. The corresponding vector will be the corresponding eigenvector of this particular thing. So that's what we are using here. Now, yes, you can skip. Now for doing the same thing for k clusters. Now we are handling the problem not for two, but for k clusters summation all the you can see here we define it for two things. So we take summation of these two. But in this case, we took summation over all the k clusters. Now, important points learned so far. One of the most important point is number of connected components is equal to multiplicity of 0 in eigenvalues of n. And other important relation is relation between optimized value of income and n, which is length. What will be the minimum value of problem we are making k clusters of this particular problem. Now, developing intuition, how this works, let's get into algorithm first. First, we are constructing similarity graph, construction of similarity graph is shown by Chaitin, and Laplacian will be again. Performance evaluation. There are many methods to perform static intervention. In general, it can be performed and give them by using the method of many other methods and very difficult the Rubik's method is best. Uh, now, we will read those points. Now, you can see that when we are using similarity methods, we are having for each point, we are having n minus 1 edges for that point. Now we want to reduce those n minus 1 information set, information set. And this will reduce it. So my claim is that for classifying most important information will be stored first thing you need to say then. So I will do the first thing as a vectors and make a matrix two out of them. Taking columns to be the vectors and now I am having a matrix n cross k. In this, each row belongs to R to the power k. So for ith point, we are using the ith row of one particular group, which corresponds to regular power k. Means you can use the k algorithm to cluster this particular points in R to cluster the original. Now, how that works. This is something I want. Now, first thing is, if we are using k-mean algorithm, finally, why are we not using it just as that is because the reasons might not be convinced. In non-convinced cases, k-mean algorithm doesn't give a good solution. But how are we so confident that the non-dimensional data set which we are considering will be convinced? That's all the technique in the world. It is the case. Now you can see that in this particular example, if you are having this particular data set, k-mean algorithm gives something solutions single testing, which is not so good. You can see. But now, if we consider eigenvectors, then right here, we will do this particular thing. And it is easy to do plus k-mean algorithm. And if we cluster this particular thing, we are able to cluster the original data. So that's how it works. Mm. Now, why are we choosing k vectors only? Why not k plus 1 vectors? See, how can we choose k? For choice of k, what we are doing is we are choosing k something is minus much greater than 0. And why is it so? Because already explained, limited k, maybe some ideal if we are taking k to 0, how much edges we need to remove? And if we want to make x one plus we need to remove much more data concentrated to play. So we will have k cases will be different for the gun. So that's why we are choosing k. Now, yeah. Here you can understand what I explained. Here you can see four clusters are here. And now just take this again clusters. And this particular thing is made by KV. Sorry. K nearest neighbor graph. And here you can see these four eigenvalues are 0. And this is non-zero. So we can conclude that they are always more interestingly, you can see it from here. Because they are from lambda 1 to lambda 5. So both more as compared to gap between these 4 points. So from here we can conclude that there will be 4 clusters, not 5 clusters in this particular graph. Now, eigenvalues there I have already. Yes. Now you can again see this algorithm, and after this particular intuition, it will be easy to understand. We can easily construct similarity graph, Laplacian graph, and calculate eigenvalues and eigenvectors. Now, if you can consider the which belongs to R and to K. Now, on that points, if K is corresponding most important information, then you can use these particular K's to form a cluster, and that will produce our original data also. Gaussian similarity function, I guess we have already covered. For constructing a similarity matrix, we need some similarity function. which we can choose to be this. Now, computational complexity, eigenvalue decomposition take n cubed and I have already told. Clustering of similarity graph. Suspecting of similarity graph takes over square times. And K-mean takes whatever time it should because it depends on number of iterations. Now, challenges and limitations, similarity, if data is huge, then as you can see, the complexity is n cubed before k-mean. So it will run into a problem that it will take a lot of time. Parameter sensitivity, it is little bit sensitive to outliers, which we can reduce by combining Gaussian and k-nearest similarity function together. And obviously it is sensitive to noisy data also. Now, practical consideration, then graph sparsity I have already told, we could combine both of those. Dimensional reduction, we could use PCH before applying this algorithm to reduce the complexity of the problem. Comparison with other methods, this is, I guess. Fifth direction is how to develop an efficient method. Like complexity is a lot more as compared to k-mean or all other algorithms. We want to reduce that particular complexity. We want it to be good towards outliers and noise and all those things. Yeah. Any questions? What?
For the naming K eigenvalues,
Yes.
there's the eigenvector corresponding to each eigenvalue.
Yeah.
So how does the vector correspond to the cluster? How do you map it?
You are taking k eigenvectors and take all k eigenvectors to be the column of matrix U n cross k. And now rows of those matrix correspond to each point. First row correspond to first point, second row correspond to second point. That's how we are mapping between those.
But finally, you point at the cluster.
Then you're applying k-means on those
Yes.
vector representations of those points.
Convex.
Yes, that
Yeah,
has vector
but that data will be in
Secondly, go back to convex.
we are applying k-means because most of the times after applying the spectral clustering, we get the convex data set. Now, it very well may be the case that it's not non-convex after applying it. That's a theoretical consideration that we need to face, but most of the times it is convex after the spectral clustering.
Okay, you have a big hat.
And AI. Okay. Using ML again is informed clustering or something like that is a natural problem, not difficult problems studied. If you are looking for mathematical basics of ML, then you will see that the clustering plays one of the key roles. Familiarizing yourself with various strategies based on proximities, based on similarities, based on properties, and based on various criteria is one of the key and foundational problems studied here. So they have taken effort to take one such one. They've gone beyond K clustering. It's a very particular and standard way of getting it done. And spectral method is one of the emerging techniques. And then the one that they have pointed out, the internet social network graph, it's only spectral methods that are more applicable in that context rather than the other means. So you can see related literature when you study those pointers that are mentioned. Yes, that also there is a great harm. The moment you are getting into them, here we are not working on deterministic properties like convexities and other things. The moment you use randomness, randomized algorithms, those properties are all completely lost. It all depends on whatever the non space that are defined by it, and then whatever is the clustering norms of creating the groups, we have to live with the groups generated by them. So that's the trade-off. Uh, yeah, in some contexts, the protocols also seem to work very effectively. We don't have a complete solution on when that would work better. It requires a bit of experimenting and working with the details to determine the right strategy. Okay, fine. Go ahead.
So the last two presentations have been quite right? I guess we all can agree upon that. No worries. Going ahead, unfortunately, the things won't be getting less rigorous because as Professor Pandurangan already said, I was just listening to him during the break because math forms the underlying math is the parent of theoretical computer sciences and algorithms in general. Right, sir? Anyways, we'll take a short right turn into computational biology. So for the next presentation, please welcome Sushmit and Anirudh. Okay. Okay, so we have looked into various computational algorithms and a bit of math, but this is a bit different. This is related to computational biology, looking into proteins. So let's understand a common problem that when it comes to protein, one of the basic problems that is protein folding. So what we are given is a linear chain. So everyone knows that proteins are made of amino acids, and initially you have a chain of amino acids, residues, which you want to initially you have a linear chain and you want to fold it. Why do you want to fold it? We will see. But what we fold it for is to get a minimum energy so that different foldings and whatever protein functions that we see arise due to this folding. So you can see a simulation of how proteins are folded. So when proteins are like when we are converting from linears to different structures, we have everyone already knows they study that they have formed secondary structures, tertiary structures, quaternary structures, and primary structures are look like this: alanine, valine, etc. So these are mainly achieved spontaneously by physical processes in our body. And so why understand protein folding? Understanding protein structures and their associated functions, as I said, there are diseases due to protein misfoldings and even due to some modifications, mutagenesis that happens. So one must understand how the folding works to predict what's wrong and how to correct it. Drug design, biotechnology applications such as enzyme design, and designing novel proteins for specific application using synthetic bio. Shout out to IGEM. So yeah, synthetic. Specificity.
Yes, so we saw that a protein is a chain of many amino acids. So a protein can take many configurations. So you can see you can have a chain, you can entangle it. So it can take many configurations. The set of all these configurations is called the configurational space of the proteins. So if you have n atoms, you can have, I mean, n amino acids. You can have the configuration space will be three n-dimensional. So you can have the coordinate of each amino acid and atom can be represented as a point in the configuration space. So at a certain instant, your protein will be a certain point in the configuration space. And when your protein folds, it will follow a trajectory in the configuration space. So in our body, the protein is initially made in a primary structure, and as it folds, it follows a trajectory in the configuration space. Now we define a construct called ensemble of proteins. So ensemble is an idealized structure, which is like you take many copies of the same system with randomly starting initial conditions. So if you find some property specific to one system, you can randomly. So this ensemble gives an idea of what the protein is doing at all points in time. Now, our protein can be modeled as a system in thermal equilibrium. And since our protein is made of thousands of atoms, we can apply statistical principles to it and so we can apply statistical mechanics to it. Now, since we assume our protein is a macroscopic system, we'll assume that it follows a property called ergodicity. So this means that if you take any two configurations in the configurational space, you can randomly, you can go from, it is always possible to go from one configuration to another with finite amount of time. And this technique randomly. By that I mean the time taken to go from one configuration to another is not same. It is random. Now, one property, so I told you what an integral is. So, if you have any physical property like energy of the protein or length between the two ends of the protein, you want to measure, you would want to average it over the different states the protein takes. So, one way you can do is you can see how it changes over time and average it over time, or you can see how it changes different what the property is in different systems in ensemble. We assume that for algorithmic systems, these two averages cannot be the same. And since our system is in thermal equilibrium, if you follow the principles of equilibrium statistical mechanics, you get the famous Boltzmann distribution for each configuration in the configuration space, and it is proportional to e power minus beta h, where h is the Hamiltonian of the protein, which talks about the total energy of the system. So this is the probability distribution of different configurations in the configurational space. And if you want to average it over the configurational space, to average any quantity, you find the quantity for each configuration and multiply its probability and average. Now you have the probability distribution and you know how to average. So one way to find these macroscopic averages would be to do brute force integration. But this would take, this is very computationally expensive because for doing a single integration, you would need to discretize your real number line and by suppose m points. And if you have n integrals to do because your dimensionality of the configurational space is n. So this would take m power n order of time complexity. So for this, what you do is you randomly sample points in the configurational space with which have high probability. So the ones which are low probability are excluded, and we assume that the protein does not reach those, don't take those states. So so how do you do this? You can do it in two ways. One is molecular dynamics, where you follow the protein in time and you sample points in the configurational space. Other is MCMC, which is Markov chain Monte Carlo. So in that you sample points based on the ensemble of realizations the protein can take. So what are Monte Carlo algorithms? So these are a set of randomized algorithms which take random samples to find, which can find potential solutions to even deterministic problems. So this is an example of finding the value of pi, where you're randomly sampling points in the square, and you find the fraction of points lying inside the circle, and from the area you find out the value of pi. So what do we do in proteins? You would want to find n MC number of points in the configurational space, which are distributed with the same probability distribution as the protein takes when it is in equilibrium. And if you find this, you can average any quantity which by finding its value at these sample points, finding it by the total number of points sampled. So how do we randomly sample these points? For this, we use a concept called Markov chains. Markov chain is stochastic process, and a stochastic process means you have a sequence of random variables which take and each random variable takes a value in the configuration space. And what Markov chains do is they have a special property called Markovian property, which says that your probability of um, uh, your random variable assuming a value in the n plus 1 state is only depending on the state before it. So you can see that the conditional probability is only dependent on the previous state. Now for a Markov chain, you can define something called transition probabilities. So since your random variables take values in the configurational space, you can define a transition probability from a state alpha to a state beta. And this is denoted by pi alpha beta. And this transition probability is a probability for changing from state alpha to state beta in the next step. So I would like to we would show you an example of a Markov chain.
So as you can see that we have taken an example where we have different types of food, burger, pizza, and hot dog, and you can see that like this thing. Yeah. So there's a probability assigned to going from either of the foods to different other foods. So we can make that transition matrix as this. So going from burger to burger, it's 0.2. Going from burger to pizza is 0.6 and so on. So the thing here is that going from one food to another, including all, so the sum of each row will be 1. And so if we look, so we will understand the stationary distribution. So at every configuration n or at every step n, we assign initially a row vector, which is a configuration at ith matrix as a row at ith configuration. And this transition matrix that we form can be multiplied with the ith row to get the I plus 1 row for our probabilities for going to one of the states. So yeah, and after some point, these Markov chains, these row matrices actually converge, and when they converge, we say that it becomes stationary. So if P star is stationary, this basically means that P star is the transition matrix times P star. So let's take our initial example. So if we have 0, 1, 0 as our initial uh, row, so when we multiply it with A, so we get another, the first configuration, and then we multiply it again to get the second, we multiply it again to get third, and so on. So at some point we reach a stationary state, as I told, and it turns out to be that it comes up, this value comes for our example. So yeah.
Right. So now we have achieved for any Markov chain, if it follows some properties, we can say that it achieves the stationary distribution. So one thing we can do is to compute the change in probabilities from one step to the next step of any configuration alpha. And if we do that, we get it as this sum. What this essentially tells is the first part is the influx of probability from different states to alpha, and the second part is the influx of probability from alpha to different states. So the change in probability would be the difference of these two. Now, when your probability reaches stationarity, these two values will be equal. That would imply that this sum would be equal. And how can you, one way to achieve this sum to be zero is to use this condition called detailed balance. When you're making the argument of the sum to be 0. And what this essentially means is the probability efflux from alpha to beta is equal to that of the influx from beta to alpha, so that the probabilities are balanced out. Now we can now how do we implement this detailed balance condition in our protein scenario? So we know that our protein is distributed in the way of our Boltzmann distribution, which is proportional to e power minus beta, e power minus beta times the energy. So and we want to finally sample points with this probability. So we know our stationary distributions ratio as the Boltzmann weights, and so this way we can define our transition matrix. So when we apply this detailed balance condition, we can get an algorithm called the Metropolis algorithm, which defines the transition probabilities, where you have a symmetric matrix times this condition, which is 1 if alpha is greater, E of alpha is greater than E beta, and proportional to exponential of the difference of energies for E alpha less than E beta. Now, how do you calculate these energies? So you can have various contributions for these energies. First one is the bond expansion. So that is the first term. Second term can be due to angular expansion and contraction. That is the second term. You can have torsional energies and you can have non-bonded energies. Non-bonded may include charge interactions or Leonard Jones potentials. And this is how you calculate your energies.
Okay, so as we looked about the Metropolis criteria, let's take that example. So just like we found the energies of of one state. So let's say you make another state, you perform a MC move, and you found the new energy, but you also have the old energy. So uh, just as Sushmit explained about Metropolis criteria, that if the new energy is less than the old energy, less than or equal to, we accept that move. But if it's the other way, we don't discard that possibility, but rather we give it a probability of accepting. So we basically take a random variable r in 0 to 1, and if r is greater than b, we accept it. So this is the Boltzmann factor that we just showed you how it came into being in a few slides ago. So let's take this simulation. Yeah, so this is basically the minimas are the shaded parts, and we have a random sampling going on, and the red arrows denote that this is rejected, this move is rejected, while the green ones basically tell that that move is accepted, and the dot is formed there. So after a while it will look like this. And yeah, so basically we're here pointing out that it will keep going on from different minimas to minima, and the most number of the density basically is present in the minimas. And this probability distribution graph that we see is almost matching to as expected. And it's not that when we are sampling, if it reaches a minima, it gets stuck there, but rather it can go from one minima to another. If you see the simulation, maybe I'll show it again. Yeah. So initially, it's our sampling is going on that minima, and later on it changes to this minima.
Right. So we now use Monte Carlo as a tool for finding equilibrium properties. That is by sampling different like randomly points in the configurational space. What we can also do is to find we can use it as an optimization tool. So one way to do this is called simulated annealing. So here you allow the Monte Carlo to happen, and you slowly decrease the temperature. And as you can see in these simulations, as you're decreasing the temperature, it converges to the minimum. And this is the famous traveling salesman problem. And when you apply this Monte Carlo optimization, you see that when temperature is zero, it reaches the optimum.
So now that we have discussed about Monte Carlo moves, let's understand how they are used in protein. So one of the ways is the standard way where we just take a atom and we translate it. So, but there is a disadvantage of this is that the protein bonds, the protein angles and torsional angles can change. So we have to take care of that so that we don't, since proteins have stiff or rigid bonds, these can lead to very unstable configurations. So let's take an example of a torsional change. So let's say we have this tryptophan present here. So initially it's in a stable way, but if we try to change it in a different angle, you see these red cylinders. So this is a simulation where it shows that these are all the collisions that are happening with the nearby residues and atoms. And this move is basically rejected because the strain energy increases a lot, and that is just another angle of viewing the same thing. So there are other ways, which is one of them is CBMC. So what we do here is take a small section of our protein and delete it. But instead of just deleting and discarding, we regrow it based on some physical configurations. So we give some biases based on Rosenblatt weights. So what here it does is we delete a section and we try to regrow it in the place based on favorable energies. So rather than trying all possible configurations of that the section that we deleted, we just, based on these biases, we add it again. And the probability for that acceptance is 1 by W new configuration by W old configuration, where this W old configuration can be calculated based on the number of possible moves, number of possible ways we can add that section upon the whole possibilities. And so another way is rebridging. So in rebridging, we alter the torsional angles in the backbone so we can move phi naught, phi 1, phi 7, and alter the torsional angle in backbone segment, then reconnects it geometrically. So we try to ensure the conformations are maintained. Another possible move is fixed end moves, where we keep the ends fixed and try to rotate the backbone torsional angles and try to maintain the internal angles present here. So this usually gives a reasonable geometric range. So yeah.
So some other applications in protein analysis. One is protein folding. You can do protein docking. You can do modeling of proteins, conformational changes. You can use it in protein design, and you can also do evolutionary phylogenetic tree reconstruction using this Monte Carlo algorithms. So this is an example for docking. What is the essential thing in docking is you have two proteins and you want to find how the complex looks, and you can follow the Monte Carlo procedure over the different configurations of orientations of the proteins and get a convergence. You can also sample different conformational changes in proteins using this Monte Carlo nodes. Yes, so yeah. Thank you. This is not mathematical. Not in dreams. Yeah. I don't want to be here.
Okay, so I guess you opened the questions.
Yeah.
Yes, so any questions? Just a minute. Question. Just a minute. This one also. Actually, if you want to, you can just go for tea because they were showing pictures of pizzas and made for some people are comfortable. You can just go for tea if you wish to, or you can stay back in case you have any questions. Also, please make sure that you be back at 3:30. I am extremely sorry that we are restricting that to only to be.
That's okay. 3:30 is fine. They can quickly take tea and then come back.
So
You have 15 minutes, that should be fine.
extension or tea?
Tea is ready. Tea is available.
That's fine.
It's normally going to a session of taking a good.
Going on there is So we did, as like, we delete a section and we try to regrow it. But so there are different possibilities, there are different confirmation how we can put that section back into it. So Rosenbluth gives some biases to different confirmation based on the energy, and we select the most optimal ones. So the W of n is basically the number of you can say favorable confirmations upon the total possible ones. So that is W of n, and based on that, he and the old configuration. So that's how you get the new configuration. But let's say you are at a state I and you want to know the old configuration also. So in that case, he retraces it back and try to get it. So basically, Rosenbluth is like a greedy algorithm, you can say. So it tries to get the favorable one at each step.
So in some sense, dealing dealing with entropy, the number of configurations.
Actually, yeah, so number of configurations and the ones which are accepted is based on energies. So both are there.
Okay, let's now break for the tea and then assemble at 3:30 or as early.
the current we are monitoring this for MCQs for knowing the available things in here. We will identify CV and so to write down the key steps and show us how MCQs principle approach to solving complex problems. Okay, let's do this one last time. Monte Carlo, one last time. Okay, so hi, I'm Sasori, and I'm with my here, and we are going to present Monte Carlo this week. So, have any of you guys played those games? Remember? Yes. I think the games most. And this is okay. I don't think if you heard of the wrong word, I don't strong in the world that Deepak good man. So, what do you think? What makes these things possible? Any guesses? Yes. But first, they are in the world we have everything. No, but sadly, so one of Monte Carlo research in it, AI there is Monte Carlo. So let's play again. Are you guys ready to play again? So let's play three cross three with Tata. Somehow bring our opinion. You said our point, what I'm going to do is fill this particular section and only have three. So you bring the cross. How many possible moves are there? Three. Great. Now, once the cross has made the move, open a circle, make the move. After this one is done. No more possible moves. This two configuration still has moves left. So this is done. This and this is left. How are you going to deal with this and this? Only one possible move. So you're done. Right? Now, if you were to determine how to win the game, this test, what would your intuition tell you? Given the particular configuration of the game, how would you decide what move to make? What is your intuition? Huh? Okay, that seems very feasible in a game like tic-tac-toe, 3 cross 3. But in a game like chess, or in a game like G, is that feasible? Mostly not. To leave that, there are only 5 steps in this kind of games. So, what kind of data structure do you think should work here? Something like decision trees? Sounds good. Now, the problem with just working out the decision trees, as mentioned by Anil, what you will end up doing is at every stage you are going to just determine what is the probability of you winning. And that can go exponentially large. That can go very large. So what's the thing? So what can be done here? Now, if you notice, I determine plus one to the win of cross, minus one to be the win of circle. So let's use these numbers to make something clever, right? So to make my life easier, not yours, of course, what I'm going to do is to represent the configurations like this. Let the black circles be the places where the cross can make move. Let the yellow be the positions where circles can make the move, right? What I'm going to do is to plug in these values into these boxes, circles. Now, here's the point. You think the right. You are playing to win, right? So, what is your intuition? You are going to play the most optimal move. That's plus one. You are going to put the value up, play that move.
Now it's the chance for the circle to make a move. And circle is playing to win. He's not, he's also a smart person. He's just playing to win, right? So what he or she is going to do is also trying to minimize, maximize his score function. For circle, it's a negative one. So it's going to minimize. Okay? And at the very end, you being a cross person here, black person here, you are trying to maximize, and hence +1. So, ladies and gentlemen, this strategy is called minimize. Now, this algorithm depends on the idea of you determining the scores. Maximizing player +1, minimizing player -1, on the type times always 0. So, as mentioned by Anil last time also, the problem of depth. So we can't determine for entire depth in this game, right? There are only possible, 100 possible moves that we can make, and we want our algorithm to go exponentially fast. So we choose that as a parameter and create a evaluation function as mentioned earlier. Sounds good? So do you think this algorithm would work in a game like that? We can't really. See the algorithm like when finite steps if possible, so doesn't really seems very stable for a very long game with a very nice person. The reason being very large time complexity, we go off onto the power D where N is the legal possible moves in that game and D being the bit that you chosen as a parameter. So to discuss further the value of these games and give a solution to this particular algorithm, I would give this mic to Cecil.
So we are saying that this universe can be very evolution, especially in games like chess and we have more problems. So what can we do? Let's revisit the algorithm again and see how it works. Yeah. So the problem with this is it is everything. That's the part of like redundant exploring. You don't want to go to all the possibilities and all. Maybe some are not necessary. So let's let me come here. So we see here, let us assume a hypothetical game where these are the rewards for the white, for the yellow, for the black player, that is this, for these things, -1, 3, and 3. So now, as the black player, we would like to maximize it. So naturally, we would take this move, which goes and gives us a reward of 3. So we get a reward of 3 here. And here we know that we have discovered this is a So as because we assume there is something. If this thing is less than 3, then because we take the maximum, this will be 3. And this will be less than 3. We know that because we take the maximum, this will be this thing, which is already 3. So in these cases, you know that this value is always greater than 3. There is a key P here. It is always greater than 3. So as I know, the opponent, he tries to minimize the reward here, but he maximize his reward. He should minimize the white's reward, the black's reward. So now he'll obviously choose 3 because it's obviously greater than equal to 5 and 3 is always less than any number greater than 5. So he chooses 3. So he chooses 3 and you never need to evaluate this part. Right. So you save up on computation time here. Let's continue. Let's assume that here it's -6 and -4. So you can see when you can here in the black screen, black circle, minus is going to be -4 because it's right. It's going to be -4 because I'm going to maximize this. Now, now we got this -4. So here, what is this? The value tries to minimize. So it obviously be less than equal to -4. But here black tries to maximize. So he'll obviously choose 3 over anything small like less than -4. So we get that the score big 3 is not needed to be evaluated. So like this, you can like remove a lot of redundant calculations and say that this directly the best possible move is this move here, like this direction. So this was used by Deep Blue, a machine by IBM, to beat the best chess player, a Russian chess player at that time in 1997. It's still not enough for Go, but it could be chess. So I want to say that pruning need not exactly work. So in the here, how we take in the previous case this is 5 and let's just assume this 2. So this was greater than or equal to 5, so we just directly tell this 3 without evaluating this part. So let us assume we interchange 2 and 5. So let's assume this 2 and this 5. So this 2, what would we say about this if we didn't know this? Greater or equal to 2, right? Now if you say this greater or equal to 2 and this 3, you can't make any inference about this thing. So then you really can't prune this. You have to find the value of this next circle. Then you can decide on what is the most optimal move. So the thing is, you want the higher reward actions to be chosen first by your evaluation function. So you want 5 to come first, then the lower 2, which needs like a good expert to say what a good evaluation function is. In chess, it's like whenever a pawn can capture a piece, that's a good move. So generally, those are the first moves it evaluates. So it can try to like maximize the pruning. So the Go is a game where it relies on intuition and you can't really do this. So this type of approach pruning doesn't work. So let's try to do a new approach, which will be MCTX. So try to like beat the best Go player. So yeah, the solution is Monte Carlo. The basic idea is explore things which are more probable of giving high rewards. So if you think that something is not good, explore it less. If you think that something is good, explore it more. As simple as such. So let's start the algorithm. The same decision tree. So this time we will be white and the opponent will be black. So we have, let's assume we have 3 unexplored nodes. I have only drawn one. So we have 3 unexplored nodes. So we have no information about it. So we'll just explore them one after one. So first we explore the leftmost one by convention. Now we have come here. Now the simulation stage. The simulation is where the Monte Carlo part comes. We give random moves for both the black player and the white player. Last time we showed we thought black moves optimally and we are trying to do something with it. Here we give random moves to black and white. So we don't care if it plays black, if black plays black, we play good. Doesn't matter. We just give random moves until we come to result. Here we get that white has one. W means white has one. L means white has lost. So we get that white has one here. So we update it here. We show that out of one game we have simulated one game it has one. This move has a mean one. Until now we have seen it always wins basically. Let's do that for the other two nodes also because we don't know anything about them. Unfortunately, they have lost their game, so it's 0 out of 1, 0 out of 1. Now, how do we choose the next one? We have to choose one of these three to say. We know that this is a good move because it won, but and this lost. But you realize that black is not playing optimally, it's just making random moves. So you cannot say that just because the 0 then it was unlucky is not lucky. So what you need is some one thing which gives you like a reward, one thing which gives you let's try out other things also. Maybe that's actually good, they just don't like because of probability. So this is called the upper confidence bound on UCD, which is defined as like mean of xi, that is here it's 1, 1 by 1, 0 by 1 is 0 and 0, plus this additional term, which is known as the exploration factor. You need to know the constant, the root square root ln n. And here is the total number of games played, which here it is 3 games. And ni is the number of games played by each one. So it is 1, 1 and 1. So here, all you need to know is exploration factor is equals to 1 and n. So if you have less number of games, this will be large. So it tries to incentivize playing the thing which are playing very nice. Because maybe you are not confident about it. That's the reason. Prioritize given which are the good reward. If you think something good, play it. Simple. So this is the thing we are going to use to select. Here you can see that this has the highest because NI is same for all three. This will have the highest UCB. And we select that like this. So here let's just assume that it has 3 nodes which is unexplored. So we again try the same thing. We explore the three nodes. First node from the left, you do a simulation, you win again. So again, what do? You update this. So that gets 1 out of 1. Also, you update the other one because it came from here. So this gets 2 out of 2. Do that for the other two nodes also, these both. So here they lost again. So here is 2 out of 4 here. Right. So here it won only 2 games out of 4. One was a direct simulation, one was it came here one, and rest these both they lost. So it's only like 2 out of 4 it won. So now we just repeat doing this again and again until we are out of time. Maybe if we allow 10 seconds for a move, we keep building as much as a tree we can, depending on computation power. We just wish on probability to give our best answer. So we do it again here. You use the selection formula. It gives you this thing in these three. Again in these three, you use your selection formula. It gives you this one. So from here, you just have this exploration again. You choose one of the three and explore and keep going. Let us assume after your 10 seconds is done, this is what you got. So this one 3 out of 8 games, this one 1 out of 6 games, this one 2 out of 5 games. I'm not hitting the lower branches because they are not necessary for deciding which move. So you see that this is 37%, this is 16%, this is 20%. So obviously you will choose the thing which has 40%. Probabilistically, this is better. Generally, you will have like maybe 10,000 games simulated, so this will be like way more, you'll be more confident rather than just 2 out of 5. But this is the possible evaluation. So you just choose. So now I'm going to give it to Sai to explain how Google DeepMind use this to be the best Go player using the program AlphaGo.
So since everyone loves to talk about ML nowadays, I'm going to speak a little about ML, how they started bringing this program. So first of all, you have to know that Go has a 19 cross 19 board, right? And has 10 to the power 170 leaderboards. So it's a very large decision tree, and even the Monte Carlo is going to be a very large tree. So the motivation was nothing but since everybody is practicing ML, so why not practice ML here too? Now the idea here is to mimic expert moves. So how do you mimic the expert moves here? By reinforcing the moves done by experts, by creating a network with slow pulse network and fast pulse network that learns to mimic move made by experts. And our routing network, of course, to decide what score to provide each node of them. Now, new reinforcement learning algorithm. It's the first MCMC algorithm, 5% of the time. So it turns out the algorithm is more like very in with most of the time. So, currently, most sensitive multi-parameter research to work right. So, with that motivation, the engineers in AlphaGo thought, okay, why not use the best of the both of the worlds? So, if you remember, in the multi-parameter research, the whole algorithm depends on the selection part. So, if only we can claim a network, select a particular node carefully, using slow policymaker, then this can help us simulate better games, right? And also you have to know this thing. Even in the simulation, we are doing things random most of the time. So simply abstract is going to make them more randomly, right? So again, using reinforcement, we are going to learn how to simulate. This is writing the simulation plans. You are exposing. Why do I am using past policy here? Since simulation takes a very large, only one to waste on learning from the French into simulation. And hence we use past policy network here and value network, of course, to determine the things. Probability. And even the you don't get to. So thanks how you use reinforcement learning and Monte research and make AlphaGo. And to know AlphaGo was Carlo was done only one person. So currently, is the second world's best player right now. Okay. At that time. So, what is the benefit of listening the all this algorithm Monte Carlo research? What are the applications? As an application in optimization, the of course. Our favorite physics simulations because it has the fact of exploration and exploitation. So, good algorithm it has. Of course, scheduling problems where you require to simulate and explore and also explore the fact that what are the beneficial nodes. It is helpful. And my favorite, planning robotics. It's helpful because once you are given the road and you don't know what particular move to make because you haven't really explored that particular map, how do you decide to choose a particular position to go? Monte Carlo research helps in that particular algorithm C. And of course, reference videos. And yeah, these are the references. Most of the reference come from MIT's video lecture on Monte Carlo research, and these are very helpful to cover very nice algorithm into. So yeah. So for further reading with data analysis, since this algorithm requires particular bandits and everything, you can actually go and read original paper of AlphaGo and this is a series from reading the PDFs to the website. So yeah, thank you and enjoy our meeting.
Practice.
Oh,
Very good.
Why were the we took the in the UG's letter? Why did you take it as lawn and divided and square root?
So the exact functions, so the functions are used so that we can use basic inequality for inverters. We just want to theoretical moment. When the theoretical
Building the algorithm itself does not really help. You need to analyze the algorithm and prove the conversions and hence this factor.
Let's see. Yeah. In same savings with GDS is different from is different from just CLS stuff.
So the problem with modular research itself is you are choosing the selection part at the very first at random, right? Now, the problem with choosing at random is not every player are going to make their move at random. Huh?
Why MPTSL? No, I'm asking. These are also different from just CNS. The CNS. Why MPTSL?
Yeah, but now the really art is even if you make the best moves, okay, the exploration factor is not there. Even though you exploit the fact that you are mimicking the expert players, you are not exploiting the fact that there are other moves that can guarantee you. There are other nodes which can be moved quickly. Multiparty this is what it does is it gives you an idea, okay, maybe this is helpful right now. Give a chance to other nodes. Something like here. Once you are done with
CNS, you like the driver node to tell you the next move, but now you're doing one layer below. Is that what you're saying?
yes.
Also about the CNNs and Monte Carlo. You know Monte Carlo, even if you don't give it a chance. If you do anything like saying, if you do like what is the winner? You know, like you might be just looking experts now wanting to
Yeah.
so like the community becomes expert not never see this. How do you make it own decision? It's not Monte Carlo.
So you have to change your output
Yeah, big
distribution.
just yeah, so like my expert is also like a good it seems like. But you know, and even your simulation, expert was also a better idea what to use it.
this part. The fast policy network helps you in the expansion part.
Yeah,
Yeah.
question.
So that,
Since you can't, I mean, in these games, you can't really go deep enough to exactly tell that this is a winning.
yeah.
What exactly does your RL reinforce or like, what does it take as a? I mean, you can't. If you could evaluate that this is a exact winning, you could have done that.
Okay.
So it tries to converge towards the expert and not towards the.
Yeah. And also here because
So it doesn't necessarily solve it.
no.
No,
No.
it just tries to mimic the expert. Like we try to mimic our teachers in terms of how the solution. Yeah, I does the same. So yeah, any doubts? Yeah.
Yeah, improve this MCDN by adding gates to the edges. Like you are going down there. Like what if you could provide possibility of each bit? If you have one by one, zero by one, zero by one, you exponentiate the chances of it fitting. So it's e raised to by one, e raised to zero, e raised to zero, add some place, provide something better. And that is generally what was done in MCMC. That's what we do, with this salience rate. We use it.
Yeah.
So the
So the thing that you are talking is it was already in the iron part. So slow policy network what CSA tries to mimic, fast policy network tries to give you the simulation. Now remember another network called value network that helps you to determine the reward company's values. Here's probability distribution using the use case there. So the idea that you are telling is already involved due to iron. So yeah, thank you.
Alright, so we use the fusion of the celebrations of the most famous events. One has you unlimited speakers that points to you, your amazing audience, and your engagement and curiosity. We have explored very creative innovative ideas and continuous techniques that shape the future of technology and production. We hope for this instrument that you something very least, given you some more, but the events we are doing is for kids. Okay, so
So firstly, Professor Pandurangan has been teaching us for the past 1 year. He used to keep telling about algorithmic thinking, computational thinking, and the math behind it. Although at that point of time we never really appreciated it. As we age forward, we tend to realize that those words of experience actually mean a lot. And the entire beauty of algorithmics and mathematics has been unveiling in front of us throughout these 2 semesters, at least for us, and probably for the seniors more as well. So, sir, we really thank you for motivating us towards that direction, and we hope this festival was a good description of how you thought we would evolve throughout semesters. So, we also have Professor through the entire term. We would like to have some few words from. Sir has been a very active support for our entire term.
yes. Yeah, so sorry, we have in the morning, missed the morning session, but at least the couple of talks that I were very interesting and very impressive that you are able to communicate very technical things in a simple way. I think I really appreciate that. Gives you feel like you understood, uh, but at least you get that, which is you get some idea of what was there. And yeah, so last year there was, I think, the sort of put up the one on paradox there, which was also very interesting. Again, inspired by Professor Pandurangan was teaching them the discrete maths course, and now algorithms. So I think it'd be great if this continues in the frame
more interesting topics going ahead. So yeah, thanks to everyone for your presentations and for coming.
I'm closing note, I would like to invite Pandurangan to challenge inspire. I'm sure one of you are already very inspired, but we are not part of the.
Yes. So, thank you very much. It's a pleasure and honor to be here with all of you. Post a retirement from IIT Madras, I thought I would go to some farmhouse and then attend some talks in college. And that's because quantum cryptography was threatening the filtering of RC. And my expertise was in digital signatures and zero knowledge protocols, which are all based on factoring. And once factoring is done and all the non-cryptography, all the cryptography that I know is broken, that I have no further future and take up something. IISc gave me a new lease of life, and they started the undergraduate program. And when they were looking for somebody who has teaching experience in undergrad, and they found me basically hanging around the post-COVID. Okay, and then I was simply pulled out here. And this being my alma mater, I graduated here in 19. I did my PhD 1977, 1982. Probably even some of your parents might not have been born that time. So, very old. I mean, in those days, I did my PhD. So, when the invitation from the alma mater came, I immediately grabbed the opportunity by both hands, and then I came here. One thing that I personally would like to do is that uh, the kind of inputs that we have both in IIT Madras and the IISc are positively skewed input. You all do a lot of preparations and you have plenty of potential. The thing to be done is converting this potential to success. How do we train? A course can be normally taught in some usual way by taking a textbook and then narrating the contents, and then routine exercises and exams can be given. And that should also be done because some grading and other things are to be done. But is it possible to take things way beyond what an ordinary textbook would cover, way beyond the routine learning? That requires a training the mind by continuous and constant challenging, advanced problem solving, and an extra credit problem, see, with incentives, some without incentive, whatever it is. But making sure that you are quite vibrant and then active in facing the challenges should be there. And nowadays, with the attitude for learning itself has been changing, your generation has got plenty of distractions, and it becomes very difficult for you to. If I compare the generation that I have been teaching, because I have been teaching for the past 45 years. So at a time there will be a student, and then we teach in the class, and anything extra they will keep thinking about it, and then corridor side here and there all over, and there is not at all a question or discussion about job and the future. None of those things. They were not blurred by any of those things, and then they could constantly involve in academic pursuit, excellence, and then even if there is no reward, they will keep doing a lot of things in an excited manner because it is interesting. But if you look at the current generation, the online reading, and there are plenty of opportunities to expand yourself in various directions. You are very explorative, you are very curious, and then open a lot of doors. At the time when we had only whatever teacher said is what is to be followed by the student, much better focus was there. Now, due to wide variety of expansion, people started going in all directions. It is not precisely the minuses. The plus is that you pursue, you have an opportunity. You get know Stanford University professors lecture on something that you like, and just like that. So what you could like, you could the flip side is that whatever you are supposed to learn and whatever you are supposed often you may miss because you will be doing something various, nothing out of your own interest. So with these kind of things, many on many occasions in the recent generation, people were missing learning certain things which they are supposed to do at that time. For instance, if you do not learn the formal proof of correctness of the algorithm through looping variants and other things, over painful or non-rewarding it look like. If you miss this point, you are never going to do it later. This point I have already mentioned. Suppose you didn't read a particular chapter in geography in your 11th. Are you going to go back after 5 years and then I didn't read this chapter, now I am going to read it and all? Never that's going to happen. Right? So the point is few things you have to learn, then do at that. So what my strategy in general, the result strategy is that insist on and then pack as much information as possible and then give as much intuition and then expose them to a lot of problems. Okay. So the the way in which the efforts that we are doing will become visible only if you do these kind of efforts. Otherwise, it will be there in some corner of the mind, like you may think that okay, it's doable, and then yeah, I think I can do it, kind of a vague feeling and nodding acquaintance you will have. But concrete action in terms of taking you to the depths of certain ideas will happen only when such things are done and only when you also rub hard way on these kind of topics. First year, they had such a fun in Paradox Festival, where we all teach in discrete math, Russell paradox, and few other things. Mathematically, very amusing. On the surface of it, it will look like clean, but then you dig a little deep, and then it will look completely conflicting. You have to dig a lot deeper to resolve that, and so on. So. The moment when I asked people to hunt around and then get it, amazing array of paradoxes were studied and presented very well. And this time, we have taken algorithms as a theme, and algorithmic thinking and other things as a theme. And when this proposal was floating around, there were a lot of volunteers. And then, as you can see in today's event, all the talks have been done exceptionally well. The details printed to them are really clean, and then the presentations were. It's not really an exaggeration to say that I have picked up a couple of tricks to say things to you from the way in which you have presented. It's honest thing. I'm not exaggerating or I'm not saying this to please anybody here. But the talks were really good. The themes that were chosen, as I mentioned already, is truly interdisciplinary. The range that you have covered and then picked up are really good. And those there are some people who are missing this evening. They have been sending messages and mailing to me like I've been watching in bits and pieces when I get time, and this is really good and all kind of feedback. And that shows that this has become a tremendous success, and may many more success of this kind be happening to all of you in the years to come. I want you to organize a lot more exciting theme oriented special seminars. Maybe it is in YAML, maybe it is in databases, maybe it is some other graphics and image processing or any area for that matter. Make sure that some extra interest and enthusiasm is shown. Learn a lot more than what is typically available in a coursework and enrich yourself. You do have opportunities like internship, project, research, and other things. But to gear well to do in those fronts, it is important that you conduct these kind of things and put yourself on to do these kind of things. Do not wait for things to come from above. It is better you take the initiative, then come forward and then seek the help and guidance of the faculty members. We are all here, very happy to help you, support you, guide you, point references, or give various pointers that would help you to learn a lot more effectively. As you might have felt at the end of this evening, kind of learning experience you had now right, is way more than what you would have done routinely in a class and other things. That is the plus point of this. But to get to this level, it's important that you go through class materials and other things properly, and then expand yourself into touching upon various research topics. All advanced research topic requires a kind of a collaborative learning. As you can see, the format of all the presentations, seamlessly you are able to transfer. Person could talk something and hand over and continue with the other one, and then although two or three people are involved, the way in which the whole thing is digested by the entire team is highly appreciated. And the same thing you must do in order to build research talent in research level reading and accomplishments are never an individual effort. For one person to read so many research papers and understand everything in their own way by their own reading is a very hard task. This is the kind of collaboration that you have to bring in research paper reading, research team based to group reading, group learning, so on. This is set a wonderful model for you how to be in a team and then learn, absorb, feed each other the intuition you have. Different minds think the same thing in a different way. And when two or three different minds converge on a theme, so many perceptions in polishing of the idea happens. The entire group gets engaged. Therefore, besides trying yourself individually to excel, forming a group and then learning together is not only fun, is the way to go for advanced reading. For a coursework material for exam, you can prepare on your own. But for research team, you need to excel in a different order. The group reading and group learning is a prerequisite. This kind of training is really open to the ways and doors for you to do things. This is set models, this is set standards. So you must impart all this spirit and learning and doing to your juniors, and a big tradition uh, must be set up. It is the responsibility of the newly mentioned students, the first, second, third, and fourth batch of students to set up the trend and tradition, the culture for IISc learning. The whole learning ambience must be rectified by these kind of books. With this few words, once again, I would like to first of all heartily congratulate all the speakers for the excellent talk and presentation that they have done. And please give a big round of applause. The first year students Pandurangan festival, and it is continuing with Algorithms festival, and then many more such festivals should light up the campus and our learning system. Okay, thank you once again. And again, before concluding, I would like to personally thank for acknowledging this event as conduits in the event, and I really, really appreciate for your gesture and the affection that you have shown. One parenthetic comment within bracket, because this is, from now onwards this has to be sincere. It's not mixing and implementation.
One thing thank IISc and CSA for supporting and helping organize this wonderful event. It couldn't have been possible without them. We'll just have one last group photo session to commemorate the festival.
Definitely, we should. Please come over here. All the participants will need to have.